Hi everyone, welcome to the stream. I know a lot of you guys have been looking forward towards this one, and me too. Um, so today we're going to talk about information geometry, its basic ideas, how do you get into the field, and is it worth studying, all kinds of questions. And I don't pretend to be an expert in the subject, far from it, but I am interested and um, and I know a lot of my viewers are also highly interested, and many of them more knowledgeable than I do. And so I hope to make this live stream into a lively seminar so we can all discuss, and perhaps I can most likely learn something from you guys as well. So yeah, let's get started. So what is information geometry? Well, let's take a look at the Wikipedia description. Information geometry is an interdisciplinary field that applies the techniques of differential geometry to study probability theory and statistics. It's quite interesting because on the surface it feels like the two fields are very much far apart. Right? How could differential geometry say anything about probability and stats, right? So that's the main question, and we will make that our main question of inquiry today. How can differential geometry say anything at all about probability and stat? Because when you typically think of probability theory and statistics, machine learning, the most common mathematical fields, the most commonly cited mathematical field, advanced mathematical fields, beyond just linear algebra and calculus, would be probably measure theory for probability, and functional analysis for machine learning, right? So how can differential geometry ever play a role here? Here's the short answer. It studies statistical manifolds, which are Riemannian manifolds whose points correspond to probability distribution. So, what is going on? A Riemannian manifold can be thought of as higher dimensional generalization of curve and surfaces in Euclidean spaces. So, in linear algebra, we studied high dimensional spaces, but those spaces are flat. In a sense, in linear algebra we study vector spaces, even infinite dimensional vector spaces, in particular in functional analysis, like the Hilbert space. Right. So Riemannian manifold are high dimensional surfaces. So the spaces are now curved, which makes geometry a lot more difficult to discuss. But still, nevertheless, it's a useful concept, right? And it has shown success elsewhere, in particular in theoretical physics. So this is a very, so to say, a very niche field. Information geometry, even to this day, it is still kind of niche. It is not particularly new, actually. It has gotten a lot more traction in the 21st century. It really started to develop in the mid 70s and 80s. But its main idea was actually already there right at the start of modern mathematical statistics. The idea of probability distribution or statistical models as manifolds. Yeah, my live stream do get saved for later. You can just click the live tab on my YouTube, on the YouTube channel. You'll see it. Hi everyone. Yeah, so this is information geometry in a nutshell. And so, as we're saying, like here, it says historically information geometry can be traced back to the work of C.R. Rao, who was the first to treat the Fisher matrix as Riemannian metric. Okay, we will discuss what this means later. Okay, the modern theory is largely due to Shun'ichi Amari, a Japanese mathematician. Actually, he was first and for all an engineer and neuroscientist. And I do believe he himself, personally, in his talk, considered himself not a mathematician but an engineer as well. So we'll treat him as such. Okay. So of course, this is rather. As I was saying, like the story is rather interesting. Like they started. C.R. Rao was one of the founders of modern mathematical statistics, right? If you take a mathematical statistics course, you've probably seen things like the Cramer-Rao inequality, to which I have. No, you're not late. We just barely started. I was just reading. Yeah, what you missed is the first paragraph of the Wikipedia page. Okay, not a whole lot. So I was saying, C.R. Rao. He was one of the founders of modern mathematical statistics, right? He worked with people like Hotelling and Fisher, and so he published the Cramer-Rao's inequality, and in the same paper, he introduced the idea of treating a Fisher information matrix as Riemannian metric. It's right at the start, and actually it was even earlier than that. Because Hotelling himself, according to the book by Amari, Harold Hotelling, famous economist and statistician, he conceived the idea of Fisher information matrix as Riemannian metric all the way back in 1929, which is almost 100 years ago. So this is all well and good. And it looks very fancy. The mathematical machinery is quite formidable, and the theory is very elegant. But even to this day, the field remains somewhat niche. Let me just put it this way, okay? Before you commit yourself into a study of information geometry, take that factor into account. So this field right now, I mean, it's been getting some traction. Let's be fair. For example, recently there's a lot more books not a whole lot, but more books being published, especially at an introductory level, towards more general. I mean, not general, but rather general in the sense of in the mathematical community, okay, audience, because. Originally, I think prior to the book by I can't even put down the date, but basically before the year 2000, I just put it that way, it was mostly just research monographs and isolated papers on this subject, and now you actually have systematic textbooks, introductory and more advanced level for this subject. So actually our plan for today is to look at two expository papers, paper/tutorial, to learn the main ideas. To learn about the main ideas, we'll do some actual derivation, and we'll spend the rest of the time on the very beginning of Amari's book, actually. Amari's book is in the stream description along with the papers. We're going to take a look at a few of them. So, as I was saying, information geometry to this day is still rather niche. Okay, it's a respectable discipline. Don't get me wrong, it's totally legit, but its application remains somewhat limited to this day. Let's just put it this way. So differential geometry was first developed by giants like Gauss and Riemann, right? Who is also a pioneer in non-Euclidean geometry. And it was first viewed as just a mathematical curiosity. Non-Euclidean geometry appeared as a watershed event in mathematics and philosophy. That the idea that the space can be non-Euclidean, right? So it was purely an intellectual sort of say, puzzle back then in the 19th century. But a major event happened in physics. Einstein formulated his theory of relativity using the language of differential geometry and tensor calculus. And suddenly, curved spaces, non-Euclidean spaces, aren't just mathematics anymore. They're physical reality. So it's entirely fair to say that differential geometry, modern differential geometry, completely transformed physics. And also in the 20th century, some parts of the applied mathematics as well. For example, in control theory. So control theory was also greatly influenced by differential geometry, in particular in nonlinear control. Things like the Lie group, etc. However, the impact of differential geometry in probability statistics and machine learning has not yet been strongly felt. To just put it that way. Why is that? Why is that? Part of it, I believe, it is historical. It is cultural, because it's just the barrier of entry is very high. The mathematical machinery required, for example, actually, I remember a quote from a professor of mine when I was an undergraduate student. So he does research in this field. He does actual research, publishes paper in information geometry, and just overall this big umbrella paradigm of the geometric approach to statistics. He does that as a professor. So he remarked the extreme difficulty of recruiting graduate students in this field. It is very difficult to recruit PhD students or even master's students into this field because the prerequisites are very formidable. So, for example, here you need things like affine differential geometry, convex analysis, and nowadays you also need algebraic geometry to do research in this field. And of course, these are way beyond the standard training of typical statistician. Right? So, of course, as I mentioned, the largest group of users historically of differential geometry are physicists, and to a less extent, applied mathematicians. But for statisticians, this is typically a very high barrier of entry. For statisticians, data scientists, computer scientists, this is a very high barrier of entry. And at the same time, its applications remain limited, that people who are well versed in differential geometry find it less motivated to apply it to probability and stat. They just, first of all, they probably also lack the background in advanced probability and statistics, machine learning, etc. Well, until recently. May I know your professor's name? Sure. Yeah, I'll just give his website. I mean, he was not my doctoral writer or anything, or graduate advisor or anything, okay? But he was in my home university, and he does research in that. Let me just give you his name. Yeah, right here. This person, Paul Marriott. You can go check out his work. So here, Professor Marriott's one aspect of his work in the area of theoretical mathematical statistics and looks at ways of applying ideas from geometry, often differential, also affine, convex, and algebraic geometry to statistical theory. Actually, I got to know the field that information geometry exists due to one of his talks at the university. Yeah, there you go. So there you go. Let me just kind of put the link in chat, all right? Anyway, so there you go. So that's the professor I was referring to. Like he he mentioned the great difficulty of recruiting graduate students in the field. Anyway, so as I was saying, because the application of information geometry remains somewhat limited. Actually, speaking of which, let's take a look at them. Here's an incomplete list: statistical inference, time series, and linear system. And these are actually mentioned. For example, time series and linear system is mentioned in Amari's book. A filtering problem, quantum system, neural network, machine learning, statistical mechanics, biology, statistics, and mathematical finance. Of course, this is a very vague list, right? In what degree and on what topic is very subtle. So, as I was saying, like here, because typically differential geometry is not part of the natural training of statistician and probabilist, and also probability stats, machine learning are usually not people who are traditionally well versed in differential geometry particularly care about. So this remains a very even to this day, if I dare to say, a somewhat natural, niche field. But we're not going to dismiss the subject because its application or progress is currently lagging behind. It was proposed or argued for in its early development. This sort of thing happens all the time. But you do need to take that into account when commit yourself into studying it. So, without further ado, because I don't have the expertise or shall we say credentials to discuss anything more substantial than that, but let's just take a look at the expository paper. Here, where is the paper? It's the second paper in the description. Here, in the stream description. It's called The Basics of Information Geometry, and this is actually written by a physicist. So it goes like this: to what extent can we distinguish the probability distribution from another? Are there any quantitative measure of distinguishability? The goal of this tutorial is to approach such questions by introducing the notion of the distance between two probability distributions and explore some of the basic ideas such as information geometry. I don't know why I put a quote next to it. It's a paper from arXiv, so it's not paywalled. Okay. Perhaps I should download this, because the resolution looks a bit wonky. Let me download this. So, information geometry by... I didn't know if you zoom in on arXiv, it looks terrible. All right. Okay, so here. Yeah, take a look at the paper in the PDF reader. So hopefully this will make the resolution a bit better. I don't need an AI assistant, man. Just close that thing off. Anyway, so here is just the list of content. You got introduction, example of statistical manifold, distance and volumes in curved spaces, two derivations of information metric, uniqueness of information metric, and the metric of some common distribution. Conclusion. So before we take a look at the main introduction, let's just take a look at the conclusion and see what kind of attitude or shall we say prediction that the author has towards this subject. It says, with the definition of the information metric, we have only scratched the surface. Not only can we introduce lengths and volumes, but we can make use of all sorts of other geometric concepts, such as geodesics. Actually, we just recently covered geodesics in our tensor calculus series. Normal projection, notions of parallel transport, covariant derivatives, we also just did that 2 days ago, connections and curvature. The power of the method of information geometry is demonstrated by the vast number of applications. Oh, really? Okay, if you say so. For a very incomplete point of entry, the enormous literature in mathematical statistics see these. In model selection and in thermodynamics, and for the extension of quantum information geometry, see this. Okay, anyway, so some applications are cited. the ultimate range of these methods remains to be explored. Okay, in this tutorial, we have argued that information geometry is a natural and inevitable tool for reasoning with incomplete information. So you see, he can be seen as a strong proponent of this field. So take that into account when you read the paper. One may perhaps conjecture that to the extent that science consists of reasoning with incomplete information, then we should expect to find probability, entropy, and also geometry in all aspects of science. Indeed, I would even venture to predict that once we understand better the physics of space and time, we will find that even old and familiar first geometry, Euclid's geometry for physical space, will turn out to be a manifestation of information geometry. Whoa. But that is work for the future. I mean, I don't see any evidence for that, but this is certainly very optimistic. We'll just leave it as such. So the thing is, the reason I mentioned that information geometry remains somewhat niche is because many of the popular and powerful statistical models and machine learning models defies the formulation of classical differential geometry. So, for example, when you talk about a Riemannian metric, we will see a definition for that, an informal definition for that, is that it needs to be positive definite. It's like a Riemannian metric is like an inner product on a vector space. So as an inner product, it needs to be positive definite or non-degenerate or non-singular, whatever you want to call it. However, for many popular models, such as the hierarchy models, Bayesian models, and etc., there is no natural way to incorporate those in a differential geometric framework. When the theory works, when information geometry as a theory works, for example, on a class of probability distribution known as the exponential family, the theory is very elegant. And it does provide insights to certain estimation algorithms, such as the expectation maximization, aka EM algorithm. But still, this doesn't feel like it is something that is quote unquote inevitable, at least to me. Or it's a nice thing to have. It's kind of like how I had a conversation with Leo lecture about category theory the other day. Like he was like his main tenet, I would say, is that perhaps the expert in category theory oversold the theory. It's not as inevitable or indispensable as it might seem, unless you work in very highly specialized field. Okay, I would say the same about information geometry. At least that's my perception of it. Okay, industry data scientists, statistician rarely mention this. Okay, but once again, let's not all be pessimistic. Let's just judge the subject by its own merit. Okay. Anyway, so coming back to the start. Well, first of all, what do you need to understand the paper? Okay, you don't need any topology, differential geometry background to understand this. All you need is some calculus, multivariable calculus, linear algebra, and basic probability. Okay. So with that out of the way, let's get started. This is perhaps the most concrete and down-to-earth and also, in a way, non-trivial introduction to the field. So I strongly recommend this paper. Is that the main concern of any theory of inference is the problem of updating probabilities when new information becomes available. We want to pick a probability distribution from a set of candidates, and this immediately raises many questions. What if we had picked a neighboring distribution? What differences would it make? What makes two distributions similar? Okay, so this is already something that in introductory statistics focused on, right? So for example, we have dedicated statistical tests for distinguishing two distributions. The most common one being the chi-square goodness of fit test, as well as likelihood ratio test. Right? So it's about telling the distribution from another. And at an informal level, you can look at, for example, the QQ plot. Right? So you have a theoretical model, and you can calculate its quantile. And then you look at the sample quantile, for example, and you plot against each other. If they roughly lie on a straight line, then roughly the two models agree. That's a first look at the problem. And then to formalize things, you can use the traditional statistical test. Right? So the idea is telling whether two distributions are distinct, okay, is a fundamental problem in statistics, and information geometry is just one approach to it. Okay, and even to this day, there are people who just use the classical approaches, and in their opinion, doing just fine. So let's see what information geometry brings to the table. It says, the goal of this tutorial is to address such questions by introducing methods of geometry. More specifically, the goal will be introduced of a notion of distance between two probability distributions. Okay, so that's interesting, right? For example, as I was saying, like you can use traditional statistical test, like a chi-square goodness of fit test. Right? The chi-squared statistic can be seen as a distance, although not mathematically speaking. Right? It's sort of a discrepancy measure between two distributions. And here we're using the language of geometry. Geometry is things like orthogonality, angles, and distance, etc., to describe such discrepancy. All right. So a parametric family of probability distribution is a set of distribution p theta of x, labeled by the parameters. So theta is a vector of parameters. So in general, there can be, well, actually in general, the number of parameters can be very, very large, and even infinite often, even infinite. Like here, we're restricting ourselves to the classical setting of parametric inference. So you have a bunch of parameters, theta 1 all the way to theta n. Like for example, the most commonly cited, commonly used model, perhaps, is the normal distribution. You have a mean and variance, two parameters to estimate. Right? And in a linear regression model, you got a bunch of the coefficients to describe the linear function or the affine function, this intercept and the slope, as well as the variance. Right? Together, basically, you form a parameter vector, theta. So these are classic models. So such a family forms a statistical manifold, namely. We're going to think about this, okay, and think about the potential restriction of this setup. Any other statistical model that is commonly used but cannot fit into this paradigm. Such a family forms a statistical manifold. Okay, we'll see what this means. Namely, a space in which each point labeled by a coordinate theta represents the probability distribution. Okay, we'll see examples for that, so don't worry if you're confused right now. Generic manifolds do not come with an intrinsic notion of distance. Exactly. So the situation for generic manifold is a lot similar to vector spaces in linear algebra. Vector spaces on its own do not carry much geometric information, except for one, that is parallelism. Because in a vector space, you can talk about scalar multiplication, right? So scalar multiplication gives you the natural language to describe parallelism, but not much else. No notion of distance, area, volume, that kind of stuff. To discuss a notion of distance, you need a norm. So here, for generic manifold, you do not have an intrinsic notion of distance either. Right? A generic manifold, basically what manifold is, in a nutshell, is that it is a space that is locally Euclidean. So if you zoom in on a manifold, it roughly looks like a Euclidean space. Much like our everyday life, living on Earth. We know Earth is curved. Hopefully nobody in this chat is a flat earther. We live on a curved surface, but in our everyday experience, things look flat. Because our normal range of activity is so small, right, compared to the global structure, right? So that's the idea. So the manifold is informally speaking, a space whose at every point it locally looks like Euclidean space. Okay, so the idea is we can consider the collection of a probability distribution as a manifold. And generic manifold here does not come with an intrinsic notion of distance. Such additional structure has to be supplied separately in the form of a metric tensor. So the metric tensor tells you, say, if you go from one point to a neighboring point, how much distance you travel. So that's the notion of metric tensor. We covered metric tensor in our tensor calculus series, but right now the exact definition don't matter. So it just tells you like how far you need to go from point A to point B, where point A and point B are close to each other. Okay, so this is an extra structure that has to be supplied separately. Statistical manifolds are, however, an exception. Okay, so here, generic manifold versus statistical manifold. Statistical manifold are exception. One of the main goals of this chapter is to show that statistical manifold possesses a uniquely natural notion of distance. A uniquely natural, actually, uniqueness is something that will come up later in the text, in the paper. The uniqueness of information matrix here. So uniquely natural notion of distance, the so-called information metric. Okay, the metric is not an optional feature, it is inevitable. Geometry is intrinsic to the structure of the statistical manifold. Let's go. Here we have the definition of the metric tensor. The distance dl between two neighboring points, theta and theta plus d theta, is given by the Pythagoras theorem. Oh, thank you very much. I mean, to be honest, I'm not teaching, okay? This is, as I said, a seminar. Questions are very much welcome. I'm just giving my own understanding. I'm not an expert in the field. I wish to learn more about it, and that's all I can say about that. So, here, the distance between two neighboring points, theta to theta plus d theta, is given by the Pythagorean theorem. So here, of course, this dl, this is a small distance, okay? We're not being super formal here. This is written by a physicist after all. So they think of dl as a tiny little distance. So from 2 points, theta to theta plus d theta is given by the Pythagorean theorem. Remember, theta is a vector. So d theta is also a vector as well. So all the components of theta can have a little perturbation. And collectively, they're called d theta, which is written in the form of a metric tensor GAB. Okay. So this perhaps deserves a little bit of explanation. Okay, so let's go back to the familiar setting of linear algebra. So go back to linear algebra. You have, say, a vector space V, and it has a bunch of basis vector, say V1 all the way to Vn. This is a basis vector. The basis vector. So you can expand any vector in V in terms of the basis vectors. This is a basis. Okay. Actually, you know what? I should probably start a dedicated note for that. First, we like to talk a little bit about the metric tensor, because this is crucial for discussing geometry between probability distribution. So here, let's go back to linear algebra. So let V actually be an inner product space. So let's say V and W are arbitrary vectors in big V, and it has a basis. So basis, just say E1 all the way to En. N-dimensional, finite dimensional vector space. Okay. Like this. This is the basis for big V. For big V. So how would you express the length of a vector? How would you express the length of a vector in V using coordinates relative to the basis? Now, first of all, what is a coordinate? The coordinate of a vector are the unique coefficients in the linear combination by basis vector. So you do a basis expansion, say for an arbitrary v in big V, little v, okay, in big V, you expand it this way, written as the sum of Ci Ei. I goes from 1 to n. Okay, and actually, guys, I'm going to use a convention, and the reason for that is a little bit involved. Basically, I'm going to use the convention that writing the coordinate using Ci subscript in this form. The reason for that is a bit involved. It's the tensor notation, okay, and the full explanation of that would take us a bit far away from our main subject. So just take a little bit of get used to. Okay, if we wanted to discuss things like power, we want to say Ci squared, we will use a bracket. Okay, this I do not stand for power. And just as a shorthand, we can write this as Ci Ei. And this is a so-called Einstein's summation convention. If you see an upper index and a lower index appear in the same equation, and summation is implied, so you can save some writing. You don't need to write the sum from I to n anymore. Usually, the upper index of the summation is fixed and is implied by the context. So usually there's no loss of information here. So this is just a basic expansion. Every student of linear algebra knows this. Okay, so what is the length? Well, the length or the norm of V, of course, is defined as such. So V norm square is V and V inner product. Okay, so V and V inner product, so let's write it this way. So this way you get the inner product of Ci Ei and Cj Ej. Okay. Of course, I and j are just dummy indices. You can change them to whatever you like. And now you have this, so to say, this is an inner product, so use the bilinearity property of the inner product. You can take out the coefficients. So now it reads the inner product between Ei and Ej times Ci and Cj. So that's the length. That's the length of a vector. And we're going to write the inner product between Ei and Ej as Gij. So you have the formula for the square length. It's Gij times Ci Cj. Gij forms a metric, a matrix. This is a matrix. This is a matrix known as the Gram matrix. So to form the Gram matrix, you just take pairwise inner product between the basis vectors. Gram matrix. Gij is called the Gram matrix in linear algebra. And from this Gram matrix, let's say if you don't know the basis exactly, okay, you don't know the basis, but all you know are the coordinates and Gij, you can still calculate length. So that's why Gij can be seen as a primitive notion on its own. Right? Once you have Gij, you know how to calculate length. Right? That's the moral of the story here. Here we introduce Gij using the basis vector, but you can discuss Gij as a primitive object. So that's why I said Gij is kind of like a inner product. And here you can actually repeat this derivation to inner product between V and W. So let's just do that real quick. So you also have another basic expansion W. W is Di, say D, maybe Dj, Ej, okay? And then the inner product between V and W can also be written in terms of the Gram matrix. So the Gram matrix really encapsulates all the geometric information that is available from the inner product. Length, angle, orthogonality, projection. You can do that with the Gram matrix and the coordinates. So there you go. So that's Ci Ei and Cj Ej. It's just so far it's just standard linear algebra stuff. Okay. So you get, oh, actually this should be D. Okay. Ci dj. So this is, of course, Gij, Ci dj. So the metric tensor, grand matrix slash metric tensor, the reason it's called a tensor is because it satisfies the so-called tensor property. Not all matrices are tensors. Okay. To be a tensor, it needs to satisfy the tensor property, that is transformation law and the coordinate change. Okay. For more detail, see the tensor calculus series. So that's the inner product. So how can we say what's the distance between v and w then? What's the distance? Well, the distance squared is v minus w norm squared. Right? According to our formula, this is Gij times the coordinate difference. So here, Ci should be replaced by the coordinate difference of v and w. So that will be Ci minus di times, actually this is perhaps a violation of the summation convention because you got repeated indices I and d and no summation is applied. So let me rewrite that. Okay, let me rewrite, say, delta Ci as Ci minus di, and then this is fine. So this is delta Ci, the difference in the coordinates, that's what it means, delta Ci, and then times delta dj, delta cj. So suddenly now this expression for the metric tensor should make sense now. Right? And we introduced the formula of metric tensor in a linear algebra setting, but you can also do it on a curved space. The situation is very much similar, and let's just see how that works. Okay, so we're going from the world of linear algebra, now going to the world of multivariable calculus or vector calculus. So recall, this is the basic setup of a surface in vector calculus. When you do when you study things like the Stokes theorem and Gauss's divergence theorem, that kind of thing, right? What do? Before you do a surface integral, you parameterize the surface. So we're going to do the same thing. So suppose this is a surface. Imagine this is a surface in R3. How do you describe the surface? You introduce a parameterization. A parameterization is a function, x, or shall we say r. R is a position vector. Okay, position vector starting from the origin, landed at a point on the surface. Okay, so that's a position vector. So position vector can be written in terms of two parameters, say u and v. So u and v. U and v are the parameters. And by setting u equals constant and v equals constant, you get the coordinate lines on the surface. So it's like on the Earth's surface, you got the meridians, right? So these are meridians are lines of constant longitude. So here on the surface, if you set u to be constant, you get, say, these families of curves. These are u constant. And you can set v equals constant too. Yeah, these are v constant curves. So naturally, this imposes a coordinate grid on the surface. Now, there's some caveat about that, okay, but at least locally, we assume we can do that. Near a particular point, you can impose such a coordinate grid. Okay, so this is rather informal description. Okay, so let's say, imagine a creature living on the surface. How do you measure distance then? Well, the distance is still understood in the classical Euclidean distance, but it's just on the surface, experienced by the surface. So imagine, this is here, this perspective is the perspective of an astronaut looking at Earth. Right? But prior to the space age, how do humans perceive distance on the surface? We would like to give a mathematical description for that. Well, so imagine a tiny movement on the surface. So here, let's say this is dr. So dr is an infinitesimal vector on the surface. This is dr. So what would dr be? Well, just use the chain rule from multivariable calculus. So dr is just partial derivative of r with respect to u times du plus the partial derivative of r with respect to v dv. So that's dr. Okay, so you can think of, what are these vectors? What is dr over du? Well, dr over du, by the definition of partial derivative, is the change in r with respect to u, the rate of change in r with respect to u when v is constant, because it's a partial derivative. So therefore, this dr over du is a tangent vector along the v constant line. There you go. This vector here is dr du, partial derivative. And here dr dv, similarly, it should follow the tangent direction of u constant curve. So this is dr dv. dr dv. Okay, so let's calculate the length of dr. So dr squared would be dr vector dot with dr vector. And what do you have? Well, you get an expansion of the inner product. It's an expansion of the inner product. And this looks like dr du dot with dr du. Right, so that's just the square length of the tangent vector. Right, the square length of the tangent vector dr du. And then du squared, use the symmetry of dot product, you get 2 times dr over du dot with dr over dv, and then du dv plus dr over dv dot with dr over dv, and then dv squared. So this is a quadratic form in the infinitesimal coordinate change du dv. And if we write the Gij, okay, Gij as a matrix, and the matrix elements are the gram matrix formed by the tangent vectors. Okay, so the tangent vectors dr du, dr dv, they form a tangent vector. Of course, this is only valid at a certain point. As the point varies, in general, the tangent vector varies, and as a result, the metric tensor varies. Okay, in a linear space, and if we use essentially an affine coordinate, if we use a constant basis everywhere at each point, then g is a constant. But it is possible to have Gij to depend on the point location. Even in a flat space, if you use a curvilinear coordinate, say if you use a polar coordinate for the Cartesian plane, not the Cartesian but Euclidean plane, the Gij will change from point to point. It's a good exercise. You can just use the recipe here to calculate g. dr du, dr dot du, dr dv dot dr du dot with dr over dv, the gram matrix. Right? We know what this is about already. But now it's just applied to a curved surface. The point is, the fundamental structure of the line element is still a quadratic form. So this is basically the metric tensor. So you can still write this as Gij, here, maybe let's write it this way, dxi, dxj, where x1, x2 are uv. Okay, x1, x2 are uv. So this is, once again, the same structure for dr squared, even on a curved surface. So that's why, motivated by this, we can consider this expression as a primitive notion. So now you're no longer confined to a vector space or a curved surface in Euclidean space. You can just treat Gij as a primitive and then use it to define a product which comes with the notions of lengths, angles, and projections, orthogonality, all kinds of things. So Gij, once again, I want to mention this is the fundamental object in the study of information geometry. Okay, so how does this connect with probability distribution? Right? We understand this equation, sort of, but how on earth does it connect, right, to probability distribution? Here, the singular importance of the metric tensor GAB derives from a theorem due to this person called Nikolai Chentsov, I believe. He's Russian. It says that the metric GAB on the manifold of probability distribution is essentially unique. This is the Chentsov theorem. And we will explain that in the later part of the paper. And up to overall scale factor, there's only one metric that takes into account the fact that these are not distances between simple structureless dot, but distances between probability distribution. So that's interesting. Of course, we're not going to prove the theorem, prove the essential uniqueness of the metric tensor, which turns out to be the Fisher information, Fisher matrix. We're not going to prove that. It's a very deep result. Okay. We will not develop the subject in all its possibilities, but we do wish to emphasize one specific result. Having a notion of distance means that we have a notion of volume, and this implies, think about this, right? Why do we have a notion of volume as well? Having a notion of distance means we also have a notion of volume. And this in turn implies that there is a unique and objective notion of distribution that is uniform over the space of parameters. Equal volume assigned to equal probabilities. Okay, so I'll be honest, I don't fully understand this sentence, but at least we can try to understand what we mean by saying having a notion of distance means that we have a notion of volume. Why is that? Well, how do we define the distance? Using basis vectors, right? Using the basis vector, right? Here, I mean, of course, here we started from the basis vector, not from the metric tensor. We derived the metric tensor as a functional of the basis vector. But think about, let's say, if you have a basis vector, if you have a basis, how do you define volume? Well, let's say, how do you define this piece of area here? Right. In regular R3, you can do something like this. You can take the cross product. You can take the cross product of dr over du and dr over dv. Okay. This is a cross product, and you take the its length. This will give you the area on the surface, which turns out to be a determinant. Big surprise, right? Determinants are volume. So basically, from this picture, you can already see it from the coordinate grid. Where once you draw on the coordinate grid, the areas are naturally described by this little lattice, these little lattices on the surface. Okay? So you have a notion of area, and this is a 2D situation. This is a 2D surface, so you have a notion of area. And in general situation, you have a notion of volume. And in fact, you can define volume element purely in terms of the metric tensor without reference to the basis vector. So once again, if you have Gij, you can express the volume element that we just described, okay, in terms of Gij alone. So that's the meaning of once you have a metric structure, you can define volume. There's a natural volume induced by the metric tensor. And this is a part actually I don't get. Guys, feel free to contribute, okay? And take whatever I say with a heavy pinch of salt for a reason I stated earlier. Oh, hi, Mala. Thank you very much for joining the stream. So it says this fact, which we sort of understand, implies that there is a unique and objective notion of distribution that is uniform over the space of parameters. I don't know why are we introducing a distribution over the space of parameters though. Are we doing some kind of Bayesianism? Which salt? The salt that I made the disclaimer multiple times that I'm a complete beginner of the field. Okay, so take my opinion about it with a heavy pinch of salt, because right now I haven't even made the decision to commit myself into studying this field. Okay, and you can scroll back to the earlier part of the stream to see why I'm so hesitant. But it is interesting. It is mathematically elegant and whatnot. But once again, I'm not a pure mathematician. I learned pure mathematics on a need-to-know basis. That's my attitude. Okay, there might be dispute over that, but that's just my attitude. Okay, I'm very much like I care about bang for buck. Okay, I'm a practical person. I care about bang for buck. I care about if I devote myself into studying X, what would be the payoff? I'm not just not restricted to monetary payoff. Okay, intellectual payoff as well, and also how it is going to be useful for the main field it claimed to help, right? Which is probability and statistics. Okay, so anyway, why do we introduce a distribution over the parameter space? Yeah, so exactly, right? So this is very strange. Perhaps if you want to do, say, Bayesianism, then certainly you want to introduce something called a prior distribution. The uniform distribution of the space parameter is called the uninformative prior. So it's equally likely to select equally likely to the prior distribution has no information whatsoever about the model, and just say, okay, because I have no information, I'm not going to discriminate any values in the parameter space, and hence a uniform distribution is imposed. Perhaps for that reason, this is useful. Right. Okay, whether such uniform distributions are maximally non-informative, or whether they define ignorance, or whether they reflect the actual prior beliefs of any rational agent, are all important issues, but they are quite beside the specific point that we want to make, namely that they're uniform. It is not a matter of subjective argument, but of objective mathematical proof. Yeah, so yeah, see, so some kind of prior belief is mentioned. Perhaps this is useful for Bayesian. Like if you want to say, describe something that is truly uniform, this could be useful. For example, guys, say, for example, let's just give a simple example from Bayesian stats. Right, so imagine you're just modeling a Bernoulli trial. Bernoulli trial. X follows a Bernoulli trial, meaning X can be either 0 or 1. X equals 1 with probability P. So let's say if you now consider a Bayesian model for this scenario, that means P itself is a random variable that should follow a distribution. But what distribution? What distribution? Well, a common distribution, a prior distribution for P is the beta distribution. Beta alpha, beta. It has certain advantages. It's called the conjugate prior. Beta distribution is called the conjugate prior for the Bayesian, in the Bayesian setup. Let me just search up the beta distribution and show you what it looks like. Okay, so the reason for choosing beta distribution is not statistical. It is purely a mathematical convenience. It's because if you use the beta distribution as the prior distribution, the resulting posterior distribution is still beta. So it simplifies calculation. Because when you introduce a prior distribution, you would have to calculate the posterior. That's P F. Density of P given X by the Bayesian theorem, by the Bayes theorem. That's the the conditional distribution of x given p, okay, times the prior distribution fp over the distribution of x, marginal distribution of x. And of course, the marginal distribution of x is an integral. And typically, the integral is very difficult to calculate. The prior distribution allows you to bypass that difficulty. So choosing the beta distribution is not mathematically, so it's just a mathematical convenience. It's not a justification. But here, imagine you have a natural notion of uniform distribution based on the geometry, right? So traditionally, if you wanted to choose an uninformative prior, you just pick the uniform distribution, beta distribution over the interval 0 to 1. Here, did I show that? I didn't talk about it. I just briefly mentioned it. But basically, this is a beta distribution, a distribution over the interval 0 to 1. Okay, and by selecting the parameters in beta distribution, you can get all kinds of shape. Okay, so for example, this tells us that beta is more likely to be in the middle, and this tells us, for example, the orange curve tells us the beta is more likely to be small. So that kind of thing. Right? So an uninformative prior traditionally is just a uniform distribution over 0 to 1. But perhaps that's not mathematically ideal. Perhaps. We could perhaps use the idea here because you can define the notion of volume once you treat this model, the Bernoulli model, as a statistical manifold. Treat this as a statistical manifold, and you calculate the metric tensor, and you calculate the volume element, and assign a uniform distribution that way. I never done that, but it does sound like an interesting idea because it removes the possibility, it removes, so to say, it removes the ambiguity when it comes to parameterizing a distribution, because P is not the only way to parameterize a Bernoulli distribution. The probability P, you can use something called the odds ratio. You can use something called the odds ratio, which is a one-to-one transform of P, to describe the Bernoulli distribution as well. So this removes the ambiguity of choosing a coordinate system. Right? This is something that geometers love. Have a coordinate-free description of an object, right? An invariance, so to say. So this is certainly has some mathematical merit to it. All right, so now let's take a look at some examples. Before I go there, I'll take a look at the chat. Yeah, thank you. Well, I'm not a professional teacher, but thank you. It has the advantage of quantifying prior knowledge of a previous number of Bernoulli trial. The reason for this is, of course, that as a conjugate prior, it is a little circular in a sense. Exactly. The reason we choose beta distribution is not statistical. Okay, it's just flexible enough and mathematically convenient enough that it becomes a convention. Okay, there's no, say, statistical optimality associated with it. It's just a trick for you to get around with calculating this difficult integral on the denominator when it comes to finding the posterior distribution. Okay, it is a convenient choice. It is a flexible choice, but its mathematical merit is very much debatable for each application. All right, so here we have some examples of statistical manifold. Okay, what do we mean? An n-dimensional statistical manifold M is a smooth, possibly curved space that is locally like Rn. What it means is that one can set up a coordinate frame that is M to Rn, so that each point, theta in M, is identified and labeled by its coordinate. Right? So theta, the set of parameters are now treated as coordinates. A statistical manifold is a manifold in which each point theta represents a probability distribution. And that's the thumbnail of the stream. On the thumbnail of the stream. So the thumbnail of the stream looks something like this. Do I still have it in my folder? I think it would be a good idea to now take a look at the stream, the thumbnail. Do I still have it? And can I show it? Yeah, here. Actually, I do have it. So this is a sample space. This is actually what you observe, right? So here, the blue distribution and the red distribution stands for two different samples. So let's say the sample space, these are the points that you observe, are visualized by these two clusters here. The red cluster, well, comes from sampling the red distribution. And the blue cluster comes from sampling the blue distribution. Now, of course, there are other distributions that aren't sampled, but still exist theoretically in the family of distribution. But now our idea is to treat a probability distribution as a point on the surface, on the manifold, statistical manifold. Because theta completely characterizes the distribution, like the mean and variance combination for the normal distribution. Okay, so now you have this curved surface, which represents probability distribution as abstract points, right? And then you can talk about, the distance between the two distribution, and now you also tangent vectors. Now this is called the score vector, by the way. It's the derivative of the log likelihood relative to the parameter. So that's the score vector. It's the tangent vector, that's why it's called S. Right? If you've seen some maximum likelihood estimation, which I assume if you're trying to study information geometry, right? So this is a score vector, basically the derivative of the log likelihood relative to the parameter, with respect to the parameter, is a tangent vector. Right? So that's the information geometric point of view of the score vector. Okay, anyway, so that's the main idea of information geometry in this little diagram here. Okay, so here we have an example. Here we have an example as the multinomial distribution. Multinomial distribution. Yeah, so, by the way, here we have this notation for the probability distribution. Okay, so that's P of x given theta. Sometimes we also write P subscript theta of x, equally valid. So that's the familiar multinomial distribution from elementary probability. Okay, so how can we visualize this as a manifold, as a surface of sort? Well, think about the coordinates or the parameter theta. They should all add up to 1 and are all non-negatives. What does this represent geometrically? This is a simplex. This is a simplex. So, for example, let's say, consider you have m equals 3. There's in total 3 outcomes. Okay, and for that you need 3 theta, theta 1, theta. Actually, you don't need 3 theta because one of them is constrained. Right. So there is a constraint among them. This is the constraint, and theta 1, theta 2, theta 3 are all non-negative. So in the parameter space, say theta 1, theta 2, theta 3, the parameter space is this little triangle in this 3D space. Not the whole 3D space because of the constraint. Actually, hold on a second. It should be strictly positive. It's strictly positive. Once again, this is something, a subtlety from differential geometry, because we don't want to deal with closed set. We don't want to deal with closed set. Makes this differentiation extremely awkward. Oh, actually, Christian, this is not n equals 2 correspond to beta distribution. N equals 2, this corresponds to the binomial distribution. Remember, this is a distribution in n, not zeta. Okay, the beta distribution is a continuous distribution here. The beta distribution is a continuous distribution for modeling something that is like a percentage, modeling a percentage between 0 and 1. The multinomial distribution is a distribution for modeling counts. Right, so let's say you have 3 outcomes, and it models the distribution of the outcome in each category. Yeah, that's okay. Yeah, so yeah, forget about Bayesianism. This is just a probability distribution on its own. There's no statistic going on. Okay, just a probability distribution. The main fact is the probability distribution is specified by its parameters, and the parameters lives in a manifold. They form a manifold. Okay, here we require all the probability to be strictly greater than 0, and the reason for that is not statistical, but rather it's geometric, because in differential geometry we hate dealing with closed sets. The reason for that is when you want to do differentiation, you always want neighbors. You want to have a small neighborhood, so you can move in all directions. A closed set, a point on the boundary, would exclude certain direction, and that's something we don't want. Okay, so that's why here we assume all the zetas are positive. It's not set here, but it is needed. Once again, this is another reason why differential geometric paradigm don't always correspond to a statistical reality. Anyway, so this is a convenient choice of coordinate, but once again, it's not the only one. No, it's not the only one. It's just like how you parameterize a surface is an arbitrary choice. Here, zeta 1 all the way to zeta m is convenient, but not unique, or quote-unquote canonical. It's just a convenient choice. So the next one is the multivariate Gaussian distribution. The multivariate Gaussian distribution, by the way, I believe this is assuming independence, or at least equal variance. Yeah. So this is multivariate Gaussian distribution. I believe, yeah, I think it assumes independence based on the form of the distribution, because there's no covariance term, there's no cross term going on here. So basically, this equals 1 over square root of 2 pi sigma squared times e to the minus, okay, x1 minus mu1 quantity squared over 2 sigma squared times all the way to 1 over square root of 2 pi sigma squared e to the minus xn minus mu n quantity squared over 2 sigma squared. Right. It's just the, yeah, exactly. So it's actually the conjugate prior is the Udriste distribution. Here n equals 2 correspond to beta. Exactly. Christian, you're totally correct. Udriste distribution is indeed the multivariable generalization of beta distribution here. Udriste distribution, it lives on a simplex. It lives on a simplex. Of course, this is what happens when you impose a distribution over the simplex. We're not doing that. Okay, we're not doing that yet, right? We're just talking about the fact that the coordinates zeta 1 all the way to zeta n describe a simplex. The dimension is m minus 1 due to the constraint. There's a sm minus 1. That's the simplex. Okay, so here in the multivariate Gaussian distribution, we should emphasize that we assume independent observations. The means may be different, but the variance are the same. This is a classic setup in the in linear regression. You assume independent observation, equal variance, but not necessarily the same mean. Typically, not the same mean. Okay, so here, what are the parameters? Well, you got mu and sigma. Well, mu is a vector, includes n component. So you have n plus 1 dimensional statistical manifold with coordinate mu1 all the way to mu n sigma squared. Okay, so that's another example of a statistical manifold. In fact, we will actually do some calculation with this one. In that case, I will assume all the mu's are the same to simplify calculation. So this way you only have two parameters, and you can actually draw some pictures, but that comes later. The next example is called the canonical distribution. This is the physicist's favorite distribution, isn't it? So this is a distribution. It's also called the Boltzmann's distribution. If there's any physicists in the chat, please correct me if I'm wrong. So this is the canonical distribution are derived by maximizing the entropy subject to constraint. So a simple scenario for that is, say you have a bunch of particles. They have a range of possible energy levels. Okay, energy levels may be discrete, may be continuous. And we wish to maximize entropy. Entropy, it has a formula, but basically it describes the level of chaos. So you want to maximize entropy. You want to maximize entropy subject to two constraints. One is the total number of particles is given, and the other is total energy is given. But the energy level, how many particles in which energy level is unknown. We try to choose a distribution of energy level so that the entropy is maximized, and to do that you end up with the Boltzmann's distribution. Yeah, exactly, it's just the Boltzmann distribution, right? So here, how can we treat the Boltzmann distribution? Yeah, as you ML guys, you know that the softmax. Exactly, this is called the softmax. So the function pi given f. Here, what is f here? What is the? I mean, I'm not talking about the meaning, but just how many degrees of freedom, so to say, in f. Well, it says we're trying to maximize entropy by imposing a constraint. The average. By the way, this is the notation of average, expected value. Okay, this is angle bracket, a direct notation from physics. This paper is written by physicists. Okay, statistician, please hold your pain. Okay, this is nothing but the expectation. You know, actually next week we'll do some stochastic processes in physics, the Fokker-Planck equation and all of that. Next, this is the Markov process in physics, the Fokker-Planck equation, Langevin equation, that sort of thing. And we'll use the physics notation. I'm mostly a stat person, so I mostly use big E. But I do understand why physicists would use this. Imagine if you use big E as expectation operator and you want to say something like the average energy. You end up having this E of big E, which is awkward, right? So that's why they settled with the angle bracket notation, which is actually kind of makes sense because the expectation of a random variable is a projection. A random variable x, if it's an L2 random variable, if a second moment exists, then it can think of as a vector in the space L2, right? And then its mean is a projection onto the space span of 1. So the projection can be written as x inner product with x, inner product with 1. And the inner product between two random variables x and y is defined as just the expectation of their product. This obviously satisfies all the inner product axiom, and that's a valid inner product. So expected value of x is indeed an inner product. So it kind of makes sense that way. You always use big E of little e for the expectation energy in physics. I guess you can distinguish the cases, or expected value of epsilon, that kind of thing, right? So yeah, but still, this notation is very much the dominant notation in physics. It drives statisticians crazy, right? And there's other things that also notationally that drive statisticians crazy. Like, you know how in statistics, the random variable is always a capital letter. I mean, as much as we can, okay? Sometimes you run out of capital letters, and you don't want to use things like big A. So you switch to Greek letter. But overall, the idea is, in statistics, we use big letter, the capital letters for random variables, and the corresponding lowercase for the quote-unquote realization of random variables, which is really just the function value of a random variable. You do that all the time in stats, but in physics, they can't be bothered. So for example, this f is the lowercase, but it's actually a random variable. So it drives statisticians nuts when seeing this. And there's no distinction between, so for example, the expected value and the sample mean. Physicists uses x bar quite often for this angle bracket notation as well. It's just you see, one of the great responsibility of applied mathematician is to promote interdisciplinary communication, and for that one needs to be bilingual and translate notations and traditions to different fields. Okay, it's kind of interesting. Anyway, so here now we have for each f, okay, for each f k, for each fk, it has its own expected value. Right, it's subject to a constraint on the expected value of n functions. So basically f1 all the way to fn. So you have n random variables, each has its own mean called fk. Okay, so the idea is you have these constraints. The constraints on the expected value are given. And of course, if you change the constraint, the distribution changes. So here the parameters are fk's. Therefore, this is an n-dimensional manifold. Okay. Once again, this is a very informal description, and near the end of the stream, I hope I'll give a formal definition of manifold that doesn't seem too unnatural. Okay. So that's the examples. So we have seen 3 examples: multinomial distribution, multivariate Gaussian distribution, as well as the canonical distribution from physics. Hopefully they all make sense why we can consider probability distributions as curved surfaces. Or so far the curved part is still unclear yet, but they can be seen as the parameters can be seen as coordinates, and the distributions that each coordinate specify can be seen as points on the surface. Okay, so now we have switched topic to just geometry, pure geometry. Okay, setting the probability stuff aside, this is pure geometry. Distance and volumes in curved spaces. The basic intuition behind differential geometry derives from the observation that curved spaces are locally flat. Yeah? Curvature effects can be neglected provided one remains within a sufficiently small region. That's our everyday life living on Earth. The idea is then rather simple. Within the close vicinity of any point x, we can always transform from the original coordinates to a new coordinate. So here, the original coordinate system xa has n components. And this is another notation. When we write something like this, if there is a non-repeated index, that is considered to be a free index. So a runs from I to n. Okay, a runs from I to n. So the original coordinate, the old coordinate, is x1 all the way to xn. So the tuple x1 all the way to xn specifies the point on the curved surface, a curved space. And now you can define a new coordinate. A new coordinate, we've been doing this a lot in our tensor calculus series. Change coordinate to x hat 1 all the way to x hat n. The idea is coordinates is just a scaffold. It's our so to say, mental scaffold for understanding a curved surface. They aren't intrinsic to the surface itself, right? But if our goal is to do geometry, whichever result we derive that are valuable should not depend on the choice of coordinate system. And that's, in fact, the fundamental idea of tensor calculus. Tensors are the key to invariance. So you change your coordinate system, but the underlying geometric object and its property shouldn't change. Right? And the thing is, it's a great tool, of course, to have a coordinate system. But at the same time, introducing a coordinate system introduces extraneous information. Right? Think about how you study a conic section in high school. Do they still teach conic section in high school? Because in Ontario they don't. I don't even know what they do nowadays. But basically, recall your high school career of studying a conic section. How do you set up your coordinate? You don't set up a coordinate randomly, right? You put your coordinate system in a way that aligns with the principal axes so that the calculation becomes more transparent. Right? But the idea is you can't always do this. Right? You cannot always a priori knows the property of an object and then impose a clever coordinate choice. You can't always do that. In general, you can't always do that. So you end up sometimes starting with an arbitrary coordinate choice, and it's unclear quite often whether a result, an equation, has geometric meaning or not. Okay, so let me just give you an example for illustration purpose. So there's something in PDE called the minimal surface equation. And what does it look like? Minimal surface equation. So imagine you have a curve in space. So you want to treat the curve in space as a boundary of a surface so that the surface is minimizing something in some sense. For example, for a soap film, you minimize the total energy. And I believe in this case, I'm not a physicist, and I believe in this case actually minimize the total area too. So what is the equation for the minimal surface? It looks like this. This monstrosity is the minimal surface equation. So this is supposed to minimize the area, but from this equation alone, it's completely unclear what the equation actually satisfies. This is the artifact of introducing a coordinate system. So this is in itself is not important, but basically the idea is if you introduce a coordinate system, equations that you derive may or may not have intrinsic geometric meaning. So that's why we have to be there's this great dilemma, right? We need coordinate system to do calculation, but at the same time, the geometric meaning becomes obscured in the process. Yeah, pretty sure it minimizes area, right? So, yeah, not around here anymore. I don't know what happened. Like, what do they do nowadays in high school? Like, conic section aren't taught anymore. So, I don't know. I mean, this is not a criticism. I'm just genuinely interested. They don't teach Euclidean geometry proof anymore. I guess perhaps that's justified because it's kind of restrictive, but not the actual content itself either. I don't know, like, what's going on. Anyway, that's a side tangent. But here, coming back, you have an old coordinate and a new coordinate. Right? The idea is geometric fact should be independent of the coordinate choice. Okay, that we declare locally Cartesian. The new coordinates is declared to be locally Cartesian and denoted with a hat with a Greek subscript, superscript x alpha. This is an infinitesimal displacement. Infinitesimal displacement, this is actually, we did that earlier here in our note. The infinitesimal displacement is just the total differential. And if you use the summation notation here, if xi, x1, x2 are replaced, u and v are replaced by x1, x2, this becomes the summation notation. So this is dr over dx1 times dx1 plus dr over dx2 dx2. All right. So by the summation convention, this is dr over dx alpha dx alpha. Okay. So that's the total displacement, a total infinitesimal displacement. What minimizes area? So here I was just giving an example. This equation describes a surface that minimizes area. So yeah, given a prescribed boundary of a surface, we want the equation of a surface that minimizes area. And the minimal surface equation, which is a PDE, gives the necessary condition for that. My point is, from this complicated equation, it is not clear that it's supposed to be minimizing area. Yeah, so that's the idea. So my point is, introducing a coordinate system may obscure geometric essence. Okay, this is not essential here. So I think we understand this equation. Yeah, we just derived it. dx hat alpha is x alpha a dA. Remember, repeated index implies a summation. Right. And corresponding infinitesimal distance can be computed using the Pythagoras theorem. So because dx hat is Euclidean, because it is Euclidean, the metric tensor is a Kronecker delta. Okay, remember, for Euclidean geometry, dl squared is just dx1 squared plus dx2 squared, which is a quadratic form. The quadratic form G as a matrix is the identity matrix. Off-diagonal terms are all 0, diagonal terms are all 1, which is equivalent to a Kronecker delta. So the Kronecker delta here comes from the fact that the hat coordinates is Euclidean. Okay, so this is that. And you can transform it back to the original frame. And transform it back to the original frame. Remember, dx hat can be written in terms of dx, so do the substitution. So here, these are all dummy indices. Alpha is summed over, beta is summed over, a and b are summed over. So that's the expression of dl squared in the original coordinate system. So now you can define the quantity GAB as this is what's that? This is Kronecker delta AB times x alpha A x beta B. So these are partial derivatives. Essentially, these are tangent vectors of the coordinate lines, which we also showed here. I mean, the same idea. Okay, this is the same idea. Okay, so we can write the infinitesimal Pythagoras theorem in the generic coordinate xa as this. This is the metric tensor. GAB is a metric tensor. So starting from the metric tensor, you can get the line element. The quantity GAB are the components of the metric tensor. One can easily go check that under a coordinate transformation, GAB transform according to this. So basically, the transformation law defines the tensor. Okay, it's not enough it's not every matrix. Okay, not every matrix is a tensor. A matrix is just a data structure, nothing else. A matrix is just a 2D array of numbers. But for a multidimensional array to be a tensor, it needs to satisfy transformation law. Here, G satisfies this transformation law so that DL is independent of choice of coordinate, which was the point from the beginning. The whole point of introducing tensors is to describe invariance. Okay, so that's the tensor property. we covered this stuff in our tensor analysis series. Okay, and now you can define the length of a curve. The length of a curve. So what happens next? So here, imagine you have a curved surface. Let's visualize that with it like a donut shape. And you have 2 points, A and B, on the surface. And you trace out a curve between them. Okay, and this curve is represented by x alpha of lambda. So that is to say, you got x1 of lambda. Lambda is a parameter of a curve. Now think of lambda as time, if you will. This is the time evolution of the coordinate on the curved surface. So you have all the coordinates, x1 all the way to xn, as a function of lambda. Once that's specified, we can calculate the total length, and not just infinitesimal length. The total length, of course, is the integral of the dl. There's typo in 11 question. I mean, I never checked this. Which typo? What do you mean by typo? I didn't check this, actually. Perhaps we should. Let's do that. I mean, if you know tensor calculus, you should be able to do that. So in our exposition of tensor calculus, we said that here, G, A, B, okay, A prime, B prime. These are prime coordinates. This is a new coordinate. Okay, prime is new. All right? Is prime new? Actually, I don't know. Yeah, there should be a hat somewhere. There should be a hat somewhere, no? But anyway, here, if GAB is a tensor, then the new GAB should be the old GAB times let me just put it this way, okay, dx over dx, dx over dx. Here, by the tensor convention, GAB, lower subscript, is called a covariant tensor. This is called a covariant tensor, and for that reason, it satisfies the covariant transformation law. That means the old tensor components multiplied by the Jacobian matrix. This is the Jacobian matrix. Okay, this is the Jacobian matrix. Perhaps I'm skimming this part too quickly because this is pure tensor calculus. Okay, this is pure tensor calculus, nothing to do with probability and stat. But basically, this tells you how do you transform from the old components of a metric tensor to a new one. Let me finish writing this up. So here, because it's a covariant, you should have d old over d new. D old over d new. So I'm going to use d old. Old is prime or what? Okay, old is unprimed. New is prime. So you should have a prime at the bottom. Yeah, old versus new. Old versus new, so therefore get prime at the bottom, b prime at the bottom, a, b on top. Okay? Once again, repeated index a and b are summed over. So invert this, what do you have? Inverting this, so you get g prime, b prime. You should get d x a prime over dxa, dxb prime over dxb, and this is GAB. Yeah, nothing wrong with that. So this is correct. This is correct. So once again, I mean, because I never explained where does this come from in this presentation. It comes from tensor calculus. Okay, if you're interested, go check it out. And I do want to make a more structured series on tensor, possibly a very long one, because I just wanted to bridge the gap between the index notation version of the tensor calculus as well as the more modern coordinate-free version of tensor. Okay, second x is, there's a typo. Oh yeah, there's a b here. Yeah, okay. Yeah, good catch. I mean, you're very observant. I pretty much just ignored and say, oh, this is fine. Sorry about that. This should be a B. Yeah, this is rather obvious, actually. Thank you very much for mentioning it. Thank you. Yeah, so we can define the length based on DL, right? Just integrate. You're just going to integrate the little length, DL, and get a total length. So that's the distance in curved space. But once again, here you have specified the arc, right? The arc is given. How do you just discuss length on its own, right? We don't want to specify a particular length. Let's just say, what's the shortest distance between A and B? In that case, you would need to use what we call a geodesic, I believe. I hope that's what's coming next. But basically, this tells us if you're given a curve, you can calculate the length of the curve, arc length. Right? And now you have this notion of a volume. You can also describe volume. Once you have a measure of distance, we can also measure angles, area, volumes, and all sorts of other geometrical quantities. To find an expression for the n-dimensional volume element dVn, we use the same trick as before. So the idea is you know what volume looks like in a Euclidean sense, right? And you wanted it to remain invariant under a coordinate transformation, right? So that's the trick here. Here, dl squared in the Cartesian coordinate, we know what it's that. We know what's that like, right? And then you use the invariance to get a formula for the general case, for the general coordinate. And here you use the same thing, right? In the hat coordinate, right, the volume element is simply the product of dx1 hat all the way to dxn hat. Right. So basically, we're taking this as well known, and then you use the transformation law using equation 6. Right. So these are details in tensor calculus. You can't ignore this, right? So right now the fundamental message is that given a curved surface specified by its metric tensor, you can define length and volume and all kinds of other things. Okay, so I'm going to skip through this, okay, because this is very much just tensor calculus, differential geometry, whatever you want to call it. I want to connect to the main subject here. All right. Okay. So as we were saying, like here, if you have this is just the final result. Okay, we're not going to be bothered with the details here. The volume of any extended region in the manifold is as such. So this is g square root, and g square root is defined as the determinant. G square root is determinant of the Jacobian matrix. X alpha A, here, remember X alpha A is this. This is a Jacobian matrix. Determinant of Jacobian matrix, that's basically the area distortion factor. Taking the square root gives you the, actually that's the area, G here, G square root, yeah, the G square root is the area, is the volume element. And to assign a uniform distribution over the curved manifold, you would have to assign equal probability to equal volume. So that's why you would have P of X to be proportional to the volume element factor. So that's interesting. And here you have an example, Euclidean space with spherical coordinate r theta phi. Actually, you know what? What's the convention here? What are the angles? What are the angles? Well, r is obviously the distance from the origin, and theta should be, okay, so this is r, okay, this looks like r sine theta, right? Yeah, that's right, this is theta, this is r sine theta. So r sine theta, imagine being swept by a small angle d phi. This is phi. This is phi. Okay, so that's the spherical coordinate. So a displacement in the space can be caused by a change in each of these coordinates, and the contributions are given as follows. So in fact, there's a little infinitesimal rectangular cube or something like that going on. Right, this is dr, and this is r d theta, and this is r sine theta d phi. Okay, so the main diagonal of this cube little thing is dl. Okay, and the volume element, right, once again, this should be familiar from multivariable calculus. The volume element is this product of those three side lengths, dr times r d theta and r sine theta d phi. That's the volume element. Okay, right. So yeah, if you want to assign a truly uniform distribution over space, you wouldn't just choose uniform in r, uniform in theta, uniform in phi. That wouldn't be uniform. Instead, the probability should be proportional to the factor here, r squared sine theta. Right. Yeah, I mean, the thing is, the physics convention for polar coordinates is different from the mathematical convention. Do you guys know that? In the physics convention, the meaning in physics convention versus mathematical convention, the meaning of theta and phi are often inverted. So be careful when you use spherical coordinates from different sources. Now, anyway, now we have circling. Now we are circling back to information geometry. So here, the previous section is purely geometric, tensor calculus, multivariable calculus, whatever you want to call it, distance and volume and curved spaces. So we're just going to take these for granted. In particular, the length formula and the volume formula. Okay, the details are a separate subject. I wonder if we end up with a Jeffrey's part. I was thinking, right? I was saying that when I was drawing this little picture here. Jeffrey's part is indeed the uninformative prior. So, but here it says we're not particularly interested in that. Right? I'm not sure if we're ever going to come back to it. But this is, on its own, just as classic differential geometry. And here let's come back to how is it connected to statistics, right? So far we established that probability distribution can be seen as curved surfaces, aka manifold. And on manifold, in general, you can, in principle, introduce the metric tensor and talk about the length and volume. Right? So far that's what we got. But here we're circling back and combining the two aspects. Okay, how do geometry show up in probability and stats? Okay, so now we have, imagine you have two neighboring distributions. In a sense that if you just perturb the parameter of a distribution by a little bit, so the original distribution is p of theta given, p of x given theta, and it's got changed to p of x given theta plus d theta. The idea is if you change the parameter by a little bit, how far, right? How far do you actually have you actually traveled, in a sense, right? So let me just consider the Bernoulli distribution once again. X follows the Bernoulli distribution P. I think it should be rather intuitive that when P is near the extremum, when P is close to 0 or to 1, if you change P by a little bit, the distribution actually changes a lot. That makes sense? So imagine P is very small. Imagine P is very, very small. It models the probability of a highly unlikely event. Let's say, P is 10 to the minus 5. If it goes from p changes from 10 to the minus 5 to, say, p equals 10 to the minus 4. The distribution are actually worlds apart, even though they all look small, right? So the idea is we wanted to quantify, say, if you go from theta to theta plus d theta, how far have you actually traveled? Well, in traditional statistics, how do you do this? How do you measure this? Well, because we know earlier that the distribution can be worlds apart, and that's our intuition. Even when the probability or the parameter changes by a little bit, because we know that, we look at the logarithmic derivative rather than derivative itself, if that makes sense. Right? We look at the logarithmic derivative. So, so here we're dealing with a general situation. Say x follows the function, a probability mass function or density function, don't matter. X given theta. Suppose you have that. What's the likelihood? Well, likelihood is just, well, equals this. The likelihood is the same. And we take the log likelihood and then differentiate. That is to say, we take d over d theta of the natural log of p of x given theta. And what is that? Well, when you take the log of a function and then you differentiate, this is the relative percentage change. I'm not sure if everyone in chat knows about it, but this should be rather fundamental and basic. So basically, let's say this is a relative percentage change. That's my point. So imagine, let's say you have a function. I know it's a little bit chaotic. I apologize. Okay, so this is you can think of it as a separate topic, but basically f of x is a function in x. The idea is d over dx of the natural log of f of x can be treated as follows. So this is the natural log of f of x plus delta x minus the natural log of f of x over delta x. Right, delta x. So here, what's the difference in the natural log? The difference in the natural log can be seen as by the logarithm rule, natural log of f of x. How do you show this is a percentage change? Use a Taylor expansion, probably. Yeah, so because the natural log of 1 plus x is approximately x, you can write it as the following. So this is f of x plus delta x minus f of x over f of x. So that's the percentage change over delta x. So that's the percentage change relative to the parameter. So that's the rate of change of the logarithm. The rate of change of the logarithm is basically the percentage rate of change in whichever quantity you differentiate. So this tells us basically the sensitivity of the distribution relative to theta. Okay? Right. That's the classic method. Right? Let's take a look at how information geometry handles this. So we would like to express the distance between two neighboring distributions. Let's imagine the probability distribution is perturbed by a little bit. So these two probability distributions, of course, correspond to 2 points. The 2 points, or more specifically, 2 coordinates, theta and theta plus d theta. Right. We would like to calculate the difference, the distance between them, given by the metric tensor. So suppose metric tensor is given, we already know how to calculate the distance, right? dl squared is just GAB d theta A, d theta B. That's basically the definition. Our goal is to compute the tensor according to P, right? Because here G is treated as given, but how does this connect to probability? So our goal is to compute G corresponding to P. And we want to do this in a natural way. We give a couple of derivations which illuminates the meaning of this information metric. I don't know, like we will see all of them, but at least we will see one of them. Okay? And its interpretation is actually quite important. We want to derive G as the Fisher information matrix. This is where we're going. Okay. And its interpretation and ultimately how it is used. Other derivations based on asymptotic inference were given in 6 and 7. Okay, so there are multiple derivations, we get it. At this point, a word of caution and encouragement might be called for. Of course, it is possible to be confronted with sufficiently singular families of distributions that are not smooth manifold, and studying their geometry might seem like a hopeless enterprise. Should we give up on geometry? No. So what does this mean? Is that what do we mean by sufficiently singular family? Here in our setup, we assume that the distributions are quote-unquote identifiable. That is to say, each point corresponds uniquely to a distribution. So each point on the manifold on the surface corresponds to a distribution. This is not always the case in reality. Sometimes you can have the same distribution, the same model, be described by two different coordinates. It is possible for that to happen. Or it is possible for, say, two sufficiently different coordinate point to represent closed distribution. So in that case, telling distributions apart become difficult. So that's the intuition of singularity. So should we do that? Right? Should we give up on geometry? No. The fact that the statistical manifold can have complicated geometry does not detract from the value of the method of information geometry any more than the existence of surfaces with rugged geometry detract from the general value of geometry itself. Okay, cool. So here we have the following derivation. Okay, I actually wanted to walk through this rather carefully because this is really where differential geometry meets probability. We seek a quantitative measure of the extent that the two distributions P of x and theta and P of x given theta plus d theta can be distinguished. So we want to derive a discrepancy measure. Okay. So here we start from the relative difference. This is something I did it earlier here. Okay, but let's follow the argument. The following argument is intuitively appealing. The advantage of this approach is that it clarifies interpretation. The metric measures distinguishability. So first, let's consider the relative difference. The relative difference is the logarithmic derivative. In typical physics fashion, there's not even a limit at the front. But basically, this years and a is what we're doing here. There's not even an approximate equal, it's just equal. Okay, I love it. Classic physicist. Okay, we get it. This is a relative difference. Okay, this is relative difference expressed as a logarithmic derivative. And here, summation convention is used in case there are multiple parameters. Okay. The expected value of this relative difference might seem like a good candidate. This is how we roll. I know, right? So calculate the expected value. Okay, this is the expected value. Okay, statistician, hold your breath. This is expectation. You can take the expectation of this quantity here. Well, this is the definition of expectation. Just dx times the density times whichever thing you want to calculate the what's that? The relative difference about. Okay. So what can we do here? We're going to exchange the order of integration and differentiation. Once again, this is purely heuristic, no justification whatsoever. Completely acceptable in physics, totally unacceptable in stats, but let's just follow along. Okay, so now after switching the order of differentiation, something magical happens. But how on earth does it happen? Well, that's just the chain rule. That's just the chain rule. So d log of p of x given x of x given theta over d theta. Okay, I'm going to omit the subscript and treat this as a single parameter for simplicity. Okay, so this is the chain rule. That's 1 over p of x given theta times dp x given theta over d theta. So you simplify that, and now p has canceled with this one, and now you interchange the order of differentiation and integral. The integral is just the integral of p. The integral is just the integral of p, and therefore is 1. So the derivative is 0. So the average of delta is 0. Right? The average of delta is 0. So in the integral may represent discrete sum of integrals over one or more dimension. The meaning should be clear from the context. And now you can, because this is 0, so the average of delta is not very informative, right? So let's look at the second moment. So this is basically the variance. Right? Here, this is the expected value of delta squared. Okay, translate that to statistician. But this is the same because mean is 0, so it's the variance of delta. Okay, it's the variance of delta. The variability of this relative difference. Okay, so now you have a double integral. You can write the integral square as a double integral. You can always do that. And this is a measure of distinguishability we seek. It has the advantage of being non-negative. Right? So this something we would like for distances is the average of delta square. Okay, so that's the average of delta square. And basically, what is this? This is a quadratic form. See, this is a quadratic form. And this thing is called the Fisher information matrix. So dl squared is now a quadratic form. Okay, so that's the dl squared. We're actually going to do a concrete calculation for normal distribution. Okay, so that's the Fisher information matrix. The Fisher information matrix plays the role of a metric tensor that distinguishes the two probabilities, two distributions. So that's what we're getting at. Up to now, no notion of distance has been introduced. Normally, one say that the reason it is difficult to distinguish 2 points in, say, the three-dimensional space we seem to inhabit, in that they happen to be too close together. It is tempting to invert this intuition and assert that the 2 points, theta and theta plus d theta, are close together whenever they are difficult to distinguish. I don't understand what's going on. I'm not sure what this is saying. It says normally one says that the reason it is difficult to distinguish 2 points in, say, three-dimensional space we seem to inhabit is that they happen to be too close to each other. It's tempting to invert this intuition and assert that the 2 points are close together when they are difficult to distinguish. I don't know what it's doing, but basically let's continue. Furthermore, being a variance, the quantity, it's a variance, so it's always positive and vanishes only when d theta vanishes. So that's also a nice thing. Only when the two parameters theta and theta plus d theta are completely the same do this distance quantity vanish. Right? So that's kind of nice. Thus, it is natural to introduce the distance by interpreting GAB as a metric tensor of the Riemannian space. This is an information metric. So now we have the Fisher information metric as a metric tensor. This is recognized by Rao, that GAB is a metric in the space of probability distribution. gave rise to the subject of information geometry. So now you have a metric, and you can do geometry. I think it's a topological. I think it's more than topological, right? You actually care about metric information. So if it's purely topological, then you only care about continuity, right? You only care about topological invariant, then that's a much broader category. Here you're introducing a metric, which is much more restricted. A metric tensor, which is much more restricted. Okay. So the coordinates theta are quite arbitrary, as we mentioned. One can freely relabel the points in the manifold. Right? Theta are just labels you attach to points in the family, in a statistical model. It is then easy to check that GAB are components of a tensor, and DL square is invariant, a scalar under coordinate transformation. So here, if you, let's say, okay, once again, this is tensor calculus. I'm going to skip that. Okay, if you're interested, look at the tensor stuff. I mean, either from me or from other creators. There's actually a lot more tensor stuff on YouTube than information geometry. So basically, that's the punchline here. The DL squared, defined this way, is an invariant. So this matrix here actually carries a geometric meaning. Okay, so that's pretty cool. We'll do this later. Okay, we'll do this derivation from relative entropy later. But let's just go down here and see the uniqueness. Yes. Right. So we managed to derive the information metric. This is very remarkable, as mentioned earlier. A most remarkable fact about the information metric is that it is essentially unique. Except for a constant scale factor, it is the only Riemannian metric that adequately takes into account the nature of the points of the statistical manifold. Okay, so once again, this is not a mathematical statement, but it does point towards the fact that the information metric is very special. Okay. Namely, that these points represent probability distribution, and they're not structureless. Okay, it's not just a collection of probability distribution that bears no relation towards each other. Okay, this theorem was first proved by Chentsov within the framework of category theory, which is actually why I got interested in category theory. They seem to pop up everywhere, even in information geometry. I have no idea. So Chentsov worked in the Soviet Union, and there was no terminology called information geometry in the Soviet Union. I believe it was called geostatistics in Russian, something like that. So his paper was completely ignored and remained untranslated for a long time. And it was only later, like after decades, that his work was discovered in the West, Chentsov. Later, Campbell gave an alternative proof that relies on the notion of Markov mapping. Okay, here I will describe Campbell's basic idea in the context of a simple example. So let's check out this example, why the information metric is essentially unique. Okay. We can use binomial distributions to analyze the tossing of a coin. Right, so once again, we're going back to the Bernoulli or binomial situation. P head is theta, and P tails equals 1 minus theta. We can also use binomials to describe the throwing of a special die. For example, suppose that the die is loaded with equal probabilities for three phases. Okay, P1 equals P2 equals P3 equals theta over 3. Okay, so together showing 1, 2, and 3 has a probability of theta. and equal probabilities for the other three phases. Okay, so the other three phases, 4, 5, and 6, together have a probability of 1 minus theta. And this then, and this binomial distribution describes the coarse outcome, low versus high, with probability theta and 1 minus theta. This amounts to mapping the this amounts to mapping the space of coin distributions to a subspace of the space of die distribution. Right, indeed. The space of the die distribution on its own is multinomial. Right, it should be a simplex. Right, here, earlier, we mentioned that the distribution, or the statistical manifold for multinomial distribution, is a simplex. And here you have 6 outcomes, right? So it's a 5-dimensional simplex. The binomial distribution, or more specifically, should be Bernoulli distribution. Okay, the Bernoulli distribution is, actually binomial. Yeah, you have n trials, big N trials. The binomial distribution lives in a subspace, which is a 2 simplex. Actually 1 simplex, because you only have 2 outcomes, right? So that's 2 minus 1, it's 1 simplex. It's just a line segment. For example, here, what would be a one? What's that called? 1 simplex on this diagram here. Can we draw that? This is a 2 simplex. Here, this is a 2 simplex. It's 2-dimensional. What would be a 1 simplex on this surface? Can we think about that? So suppose you have a constraint, an extra constraint among theta 1, theta 2, theta 3. But apart from the most general constraint, there's also an extra constraint. For that to happen, it basically means a curve on the simplex. Basically means a curve on the simplex. And I believe one example for that is I think it's called the Hardy-Heisenberg model in genetics. So basically you make use of this identity here. So theta plus 1 minus theta squared is 1. Expand that, you get theta squared plus 2 theta times 1 minus theta plus 1 minus theta squared. And you're just going to call these 3 terms theta 1, theta 2, theta 3. Of course, by default, they satisfy the constraint. But now you have a curve on the simplex. So that's a subspace or a submanifold on the big manifold. Okay, you get the idea? So yeah, this is a special parameterization of a curve on the simplex. So basically, here we have a similar situation. The die distribution, the space of the die distribution is a simplex S5. The space of coin distribution is a simplex S1. Yeah. So this is an embedding. The embedding of the statistical manifold of n equals 2 binomials, which is a simplex of S1 of dimension 1, into the subspace of the statistical manifold of n equals 6 multinomial, which is simplex S5, is called a Markov mapping. Having introduced the notion of Markov mappings, we can now state the basic idea behind Campbell's argument. Whether we talk about heads or tails outcomes in coins, or we talk about low or high outcomes in dices, binomials are binomials. Whatever geometrical relations are assigned to distributions in S1, exactly the same geometrical relations should be assigned to the distribution in the corresponding subspace of S5. Let's reread this. whatever geometrical relations are assigned to the distribution S1, yeah, in the one simplex, exactly the same geometrical relation should be assigned in the distribution in the corresponding subspace of S5. Okay, so here imagine the S1 is just a line. It's just a line segment. This is S1. So imagine this is S5, okay? This is S5. So the embedding of S1 through the Markov mapping must be something like this. So the idea is it's like if you put S1 onto a different piece of paper, the geometric property of S1 should not change. I think that's pretty intuitive. Right? Therefore, the Markov mapping are not just embedding, they're congruent embedding, or congruent. How do you pronounce this? Congruent or congruent? I always say congruent. Put the stress in the first syllable. Okay, so they're congruent embeddings. There's rigid motion, basically. The distance between the distribution in S1 should match the distance between the corresponding image in S5. Okay. If you pick 2 points in S1 here, and you use the embedding map, the distance in S5 should be the same as in S1. And now for the punchline. The goal is to find the Riemannian metric that are invariant under Markov mapping. Okay, so now we're not assuming Fisher information or anything. Okay, these are, remember, S1 and S5 are just manifold on their own. They it's a line segment or a triangle looking thing. They don't intrinsically carry metric structure. But let's just say if we want the Markov mapping to preserve distance, if we want the Markov mapping to preserve distance, what sort of distance should we assign to these spaces? Right, so that's the punchline. The goal is to find the Riemannian metric that are invariant under Markov mapping. It is easy to see why imposing such invariance is extremely restrictive. The fact that distances computed in S1 must agree in the distance computed in a subspace S5 introduces a constraint on the allowed metric tensors. But we can always embed S1 and S5 in spaces even larger and larger dimension, which leads to more and more constraint. It could very well have happened that no Riemannian metric survives in such restrictive condition. It is quite remarkable that some do survive, and it's even more remarkable that up to an uninteresting scale factor that the surviving Riemannian metric is unique. And it turns out to be the Fisher information metric. So that's the idea of uniqueness. All right, so why don't we, you know what, get our hands dirty and do some calculations. Here are some calculations. I think it would be great practice, huh? Let's do those calculations. Actually, guys, I'll do a poll in chat. Should we do the calculations, get our hands dirty, and look at another paper? Or perhaps Amari's book of content to see where things are going? Yeah. So, chat. Shall we get our hands dirty and apply the formulas and do the calculations just like our regular, more mathy streams? Like, or should we look at a different paper to stay at a high level? Any idea in chat? And actually, let me go grab some water because I've been talking for some time. I'll be back in a minute. All right. All right, I'm back. You like to see a bit of a dirt. Okay, great. Calculations. Let's do that. Okay. Chat unanimously decided want to get their hand dirty. Let's go. I love it. So here we have, starting with the multinomial distribution. Okay. So let's try to follow this and write it ourselves on the side. So starting from the multinomial distribution, what do we want to do? We want to calculate the metric tensor G, right? What's the general definition of G? Going back to the big formula. Essentially, you just want to calculate the Fisher information matrix. Right? So that's what you want. GAB theta definition is this thing. Once again, in classic physics fashion, in integration, dx is at the front. Only physicists do that. I don't think engineers do that either. It could be argued that if you have a long expression you want to integrate, it's easy to forget about the dx, so you just put dx right at the start so you don't forget about it. Okay? It looks awkward as hell, I mean, to me at least, but anyway, this is a big log, not a big log, d log of p x given theta over d theta, and here you have a. Summation is implied, by the way. Actually, no summation. This is free index, no summation. And then d log of p of x given theta over d theta b. Okay, some concrete calculation. So let's apply this formula and see how do metric tensors look like for things like the multinomial distribution. Okay, here. Well, this is the probability mass function. Here, little n is a list, n1 all the way to nm. Okay, but for the sake of calculation, you can treat little n as constant. No. So I have time until 12, so an hour and a half. Okay. Perhaps at the very end, we will take a look at the list of content by Amari, by Amari's book, and we will wrap up the stream and discuss, if you want to pursue it, what would be perhaps a reasonable route. Okay. The good news is you certainly don't need a comprehensive study of differential geometry to get into the field. Okay. So yeah. Just like stochastic calculus, I should probably add a new episode in that series. Right? You don't always need the full machinery of measure theory to do stochastic calculus. You don't need the full machinery of differential geometry to do information geometry either. Here, you have, starting from the probability function, you got the constraint, you got the, here actually, you know what? Are we treating all of them, all of the thetas as coordinates, or just m minus one of them? Yeah, I think m minus one of them. Because if you treat all of theta as coordinates, you end up with a singular g. Okay, so here we only differentiate with respect to the quote-unquote free parameters. Okay? So it says the result is this one. Okay, we'll try to derive this. Okay, here in the multivariate normal distribution, Pn n given theta. Let's say if we fail to do this for the general case, we will do this for theta 1, theta 2, the two parameter case. How about that? If we don't manage to derive the general formula, let's do the restrictive case. But here, let's start with the most general situation. Nm, multinomial. Okay, so little n is n1 all the way to nm. With sum of ni, I from 1 to m equals big N, and the sum of theta I from 1 to m equals 1. So we have this model, and now we wish to apply the formula. Okay, in the formula, the integration should be a summation. So GAB of theta, there should be a sum. The summing over what, right? It should be summing over all possible little n. Because this is meant to be an expectation of sort. You should sum over all the tuples little n. So here we would put the probability function and the natural log derivative. Okay, so you got d log pn. Why there's a big N here? I guess N is appear here. I guess we can get rid of the big N to save some writing, because N is a constant anyway. Perhaps we'll do that in a bit. Okay, so that's the function we want to differentiate. Okay, so take the log of Pn of n given theta. What would that be? The good thing is this constant can be simply ignored because differentiation kills it anyway. So it's constant plus n1 log of theta 1. Theta 1, is that the same notation we've seen in the here? Oh, actually we use Gij. Let's follow the same indices, Ij. Ij, okay, theta I, theta j. And Ij are from 1 to m minus 1. Okay, and now we take the big log, right? Not the big log, just the log. Okay, take the log. Here you got n1 log theta 1 plus all the way to nm times log of theta 2, theta m. Yeah, so that's the log. And then you differentiate d over d theta I. D over d theta I. This gives us Pn and given theta. So only one term survives after differentiation. So this is just ni over theta I. Yeah, that's just ni over theta I. And how do you calculate the this sum, huh? In statistics, as always, the most difficult part is calculating summations and integrals and that kind of stuff. Moment calculation in general is very difficult. So here it looks like, if we write it as an expectation, it looks like we're calculating the expectation of ni over theta I times nj over theta j. Right? Oh, actually, guys, I think I missed something. Because here we're only considering ij from 1 to m minus 1 as the free parameter. Theta m should be expressed in terms of them. Theta m is not free. So the last term should be nm times the natural log of 1 minus theta 1 minus all the way to minus theta m minus 1. Because if I don't do that, I'm missing a term. So it should be ni over theta I, and then what? And then nm, the last number, over 1 minus theta 1 minus all the way to theta m minus 1, theta m minus 1, and was what? With a minus sign, because theta I has a minus sign at the front, just the chain rule. So this should be the derivative. Okay, and of course you can write it as ni over theta I minus nm over theta m. Yeah, that's better. That's a lot better actually. So Gij, element Gij in the metric tensor is ni over theta I. Guys, I think I messed up the indices. Yeah, this is such a difficult habit to break. Theta I should be upper index, should have upper index. Coordinate uses upper index. This is what happened when you're not a differential geometer or theoretical physicist. You're just so used to writing coordinate index as subscript. In differential geometry and in GR, the numbers are, the coordinate numbers, coordinate labels are upstairs. Difficult to get used to after years of habit. Okay, let me fix that because that's bad habit. Okay, so now that looks better. Oh, by the way, do n uses upper or lower index? I'm not sure. Let's take a look at the lowercase. Okay, lowercase. Okay, sure. Yeah, let's use lowercase. Hold on a second. What are we doing? Oh, we are actually using lowercase as well. This is terrible. This is inconsistent. My goodness, I hate it. I hate it so much. You see, this is uppercase. Why are you doing this, physicists? These are uppercases. My goodness. You see, they should be uppercases. They should be uppercases. Or, you know what? Screw it. Let's use lower cases just to look exactly the same as the paper. Okay. I mean, in this calculation, it probably does not matter. But for if you're changed to a new coordinate system, then you're in trouble. Okay. But what else can I say? So there should be it should be upper cases, but then here in the calculation we use lower cases. Thank goodness we're not doing any coordinate transformation in this example. Okay. And now I change it. I have to change everything back. Okay. All right. Apologize for my frustration. So theta 1, theta I minus theta m. So now looks better, huh? Everything is consistent now. Okay. So Gij is the expectation of ni over theta I minus nm over theta m times nj over theta j minus nm over theta m. Okay, there's that. So for that, you're going to need some property from the multinomial distribution, and I think we can just quote it from the table or whatnot. Okay, so we're not going to derive the properties of multinomial distribution from scratch, but from here you can already pretty much get the result. That is, you need the expectation of, say, this is let me expand that carefully. 1 over theta I theta j, expected value of ni and j. Okay, and then minus here 1 over theta I theta m, expected value of ni and nm, minus 1 over theta m theta j, expected value of nm and j, and then plus the expected value of nm squared over theta m squared. Okay, and we can look for the product moment in the property of multinomial distribution. Let me go search it up. Nomial distribution. Here. This is a covariance. This is a covariance. From the formula of covariance, you can deduce the product moment. Can we perhaps look at the property here? Just the product moment. Can we get that? Okay. So anyway, we have the covariance. So that should be enough information. So from this formula, actually mean variance are both needed. There you go. This is from Wikipedia, and the notation, just want to make sure we're consistent here. Yeah, okay, so that's the PMF. So we can use these facts to recover the expected value of, hold on a second, does the paper even simplify? Oh, it actually didn't. Oh, it does simplify. Here we get this is the correct expression, the expectation, right? And now we need to simplify to this thing, and that will finishes the derivation. Okay, so here from this formula given by Wikipedia, expected value of the product is the covariance. Remember, covariance is the expected value of the product minus the product of expectation. So that will be the covariance of xi xj plus exi exj. Okay, so that's the covariance of minus n pi pj plus n pi n pj. Okay, so this will of course be minus n squared. Maybe just do it this way, say n squared minus n times pi pj. Okay, so we have everything we need now. But just as a verification, okay, so let's say if I and j are the same, expected value of xi squared is what? Oh, actually this only works when I and j are not the same, so this verification is meaningless. So yeah, this is I naught j. This is not I naught j, but we need a expected value of something squared. Okay, we need that. So the expected value of x I squared is the variance of xi plus the expected value of xi squared. Okay, the variance is here, is npi times 1 minus pi, and plus the square, okay, which is n squared pi squared. N squared pi squared cancels, it seems like. Yeah, it's just npi. Double check. Oh, actually, no. No. It doesn't cancel. Instead, this is npi minus n pi squared plus n squared pi squared. There's that. Yeah, that's correct. Okay, so this is definitely not a special case of the first one. All right, so let's continue here. You get 1 over theta I theta j using the product moment formula. Okay, I and j. You gotta distinguish whether they're the same or not, right? Whether they're the same. Okay, so let's do the two cases. So for I, let's do the simple case once. So I equals j. Diagonal elements first. Gij is 1 over theta I squared. Right, Gii is 1 over theta I squared times, the second moment of ni. The second moment of ni by the formula here, little n is our big N. So that's big N times theta I minus theta I squared, big N, plus big N squared theta I squared. Okay, so that's the first term. The second term is 1 over theta I theta m, okay, and use the product moment formula. My goodness, I hate this simplification. You see, this is very tedious, but it should be straightforward. N squared minus big N, n squared minus big N, pi p theta, that would be here, p I, yeah, theta I theta m. Okay, theta I theta m cancels, it seems. And this is minus 1 over theta m, theta j, and here you have expectation of, this should be the same as what we have earlier, big N squared minus big N times theta m theta j. Okay, and finally plus 1 over theta m squared e n m squared, so that's the moment of this thing. So we have big N theta m minus big N theta m squared, and then plus big N squared theta m squared. Okay, to simplify this, what do we have? Well, you got big N over theta I minus big N plus big N squared minus big N squared minus N minus big N squared minus N. It looks like there's some cancellation going on, which is great news. Big N over theta m, big N over theta m, and then minus here a big N plus big N squared. Okay, so yeah, only two terms survive, so that's big N over theta I plus big N over theta m. So let's compare this with the answer in the paper. Yeah, indeed, this is true. When delta, here, this is the Kronecker delta, when I equals j, you get the answer. Right, so yeah, I think I'm gonna skip the case. So yeah, for I not equal j, left as exercise to the viewer. This is just big N over theta m. So that's the Fisher information matrix. Actually, you know what? Let's see if the Wikipedia page have that. Usually have that. Fisher information matrix is a common distribution characteristic. It's not here, huh? Apparently it's not here. Let me find it. Fisher. No, there's no Fisher information metric here. Okay, so that's a concrete calculation for the metric. Let's think about the potential difficulty when it comes to applying this. In the beginning of the clip, you say there's vector space, there's no intrinsic concept of distance. What does intrinsic mean? I would cosine similar. Oh, yeah. Why do you extract? That's a great question. Why do you retract that? Okay. So by that we mean it has to do with how mathematical notions are defined. Okay, it has to do with the axioms of vector spaces. I was drawing an analogy from linear algebra. So going to, for example, I'm going to pull out Axler. Whenever there is a confusion about notions of linear algebra, we go to Axler, okay, to cite the definitions here. For example, here, just in the vanilla vector space, do we see any notion of distance here? A vector space on its own. It only has the prop here. What's going on? Vector space definition of vector space. Yeah, it only has two operations: addition and scalar multiplication. There's no notion of a distance on the vector space, right? There's no intrinsic notion, and this is in particular very important when you talk about function spaces. For example, on the space of function, you can consider things like the L2 distance. L2 distance, which is essentially an integral, to measure the distance between two functions. Or you can use the soup distance. These are arbitrary choices that depend on the priority of the user. A vector space on its own, it only has two operations, addition and scalar multiplication. Addition and scalar multiplication satisfy a bunch of property, but there's no notion of distance on the vector space on its own. That makes sense? Yeah. No worries. Yeah. Like, come on, let's not worry about grammar in a math stream. I say grammatically nonsensical sentence all the time, and I'm unashamed. Okay, perhaps I should. The thing is, there's no notion of distance intrinsically that comes with a vector space. Okay, here in linear algebra, we typically introduce the notion of length in the context of inner product spaces. Once you have, here it says, in making a definition of vector space, this is perfect, we generalize the linear structure of R2 and R3. We ignored geometric features such as notion of length and angle. These ideas are embedded in the concept of inner product. So I always make this analogy of inner product spaces versus vector spaces. Think about buying a car. If you just buy the most basic model, okay, basic model of a car, it just gets you from point A to point B, that's it. And if you buy a luxury model of the same, from the same family, so to say, upgraded version, it comes with more feature. So that's essentially the relationship between inner product spaces and vector spaces. With the help of the vector space, with the help of inner product, then you can talk about norm. That's length. And with the help of a norm, you can talk about distances. So basically, that's that extra feature you add to the vector space so that you can talk about geometric features like length and angle. In Euclidean geometry, the length is a primitive notion.
in Euclidean geometry, angles and lengths are undefined. Euclid treats them as self-evident. But in the linear algebra, vector spaces by default only comes with two operations, addition and scalar multiplication. Whereas things like inner product and norm are added on it to allow for a richer theory. The same thing is true for curved surfaces. So for curved surfaces, actually, so we're talking about manifold. Okay, so we're talking about manifold. So a curved surface on its own, it's a manifold. So this is a rather generic introduction. Perhaps we should spend the rest of the stream, a little bit of the rest of the stream on the discussion on how to define a manifold. Okay. So basically, think of this is an abstract space that is quote-unquote curved. A manifold on its own only needs to be locally Euclidean. So that means at each point there is a neighborhood, okay, that can be mapped in an invertible way to a Euclidean space, to a subset of Euclidean space. It doesn't even need to be the whole Euclidean space. This is all it needs. You want to make sure that the map is invertible. Okay, it's like literally a map. It's literally a map to describe a region on the Earth's surface. So that's all you need to define a manifold. You need local neighborhoods of a curved surface to look like a Euclidean space, to approximately flat. That's enough. Okay, but there is no information about how do you calculate distance on the manifold. There's no such information. So there's a hierarchy of manifolds. So first you have the topological manifold. And then you have the smooth manifold. So topological manifold allows you to talk about continuity. Smooth manifold allows you to do differential calculus. And finally, we have the Riemannian manifold, which is a subclass of the smooth manifold. These are all nested. Okay, Riemannian manifold is a special case of a smooth manifold. Smooth manifold is a special case of topological manifold. So Riemannian manifold is a smooth manifold that allows you to have a notion of length with the help of a metric tensor. Yeah. I think for most distribution you only need a single coordinate chart. I don't know, like I haven't seen enough examples of it. But in general, you can have multiple coordinate chart. And for topological reasons, sometimes you need multiple coordinate chart because it's a simple fact that you cannot map you cannot map a circle. You cannot map a circle with a single coordinate chart, right? Because the region on Rn is open. For us to do differentiation, you need an open set here. And the unit circle is compact. So there isn't a continuous function that maps bijectively. There isn't a homeomorphism that maps from an open set in Rn to a compact set. So even for something as simple as a circle, you need more than one chart. And I believe there should be situations similar to this in probability distribution as well. Although here earlier we only deal with one chart globally. Okay, well anyway, that's perhaps a little bit of a digression. Okay, and speaking of which, I think it's a good time for us to go to another paper, okay, that delves into a more careful definition of a manifold. So let's go. So here, this one. So actually, this is the first link in the stream description. It's called an introduction, gentle introduction to information geometry. Okay, I love it. So, background, differential geometry. So first, I mean, here we're going to be a little bit more formal. Okay, earlier we just talked about vague analogies of high-dimensional spaces, coordinate system without being very precise. But that's okay. Here we're going to talk about things a bit more formally. So here, top coder. So what Christian mean is that you need more than, sometimes you need more than coordinate chart. Coordinate chart is, as we'll see here. So bear in mind, so be a little bit more patient, and we will see the definition of a chart here. We'll see a definition of a chart. Do we have this? There should be chart. Yeah, the chart. Okay. So it has nothing to do with the number of parameters. The number of parameters is the dimension. The number of parameters needed to describe, to parameterize the number of coordinates needed is the dimension of the manifold. The number of chart is different. Number of charts. So think of a book of map. It's called an atlas, right? It's literally called an atlas by cartographers. So if you want to describe the surface of the Earth, right, you need a book of maps called an atlas. And of course, each page of that book is a two-parameter parameterization of a region of the Earth. Right? You need two independent coordinates, longitude and latitude, to describe a point on the surface. So that's the number of parameters needed. That's a dimension. But the number of charts, you can have as many maps as you like. Right? As many maps as you like. Here, mathematically, the only requirement is that all those charts together describe the full manifold, describe the full Earth. And those chart needs to be mutually consistent. So let's say if you have two charts describe the same region, they should correspond to the same region on the manifold. So let's say if you have a map of Asia and a map of Europe, well, Russia is both in Europe and in Asia, so that's included in both maps. But of course, the same region on Earth is unchanged, right? So if you have two pieces of chart describing the same region, that is to say, if two charts have overlap, they should satisfy a compatibility condition. So that's the only mathematical requirement. You can have as many charts as you like. The book of maps can be as thick as you want. So that's basically what Christian is saying. Okay. Yeah. And as the circle mathematically needs two charts due to topological reason. We'll see perhaps in these notes. Okay. So it's very subtle actually. The definition of manifold is quite subtle. We'll motivate that along the way. Manifold. The geometric shape that we're most familiar with is Euclidean or flat space Rn with the Euclidean distance metric. Okay, so this is just the classic distance formula we know from high school. A manifold M is a space which is locally flat. Okay, so this set can be an abstract set. It doesn't have to be a subspace. It doesn't have to be a subset of Rn. Okay, quite often, interesting manifolds are not subspace of Rn. Things like matrix groups. they aren't naturally embedded in Rn. So we're just going to treat M as an object on its own, without any kind of extraneous information. So M is an object on its own. So we wish to formalize the notion that M is locally flat. And to do so, we need some concepts from topology. So topology allows us to talk about nearness, right? Because manifold, as we said earlier, intuitively, it is a space such that at each point, its neighbor looks flat. But what is a neighbor? What is a neighbor? So this is the definition from topology. Topology allows you to talk about nearness formally. A topological space X is defined by a set of points, X in big X, and a set of subsets called neighborhoods for each point. And a neighborhood obeys some axiom which allows for consistent concept or locality. So now we aren't defining what neighborhood actually are, but just a set of axioms. You know, it's like in Euclidean space, you have the definition of neighborhood as a circle, basically. This is what we call neighborhood in Euclidean space. That's a concrete definition. Often we write epsilon neighborhood. Okay. And inspired by some of the properties of epsilon neighborhood, in Euclidean space, we can define neighborhood abstractly. Okay. We're going to define neighborhood axiomatically. So these are all considered as neighborhood. Neighborhood obeys some axiom which allows for a consistent concept of locality. So these are, if U is a neighborhood of X, if U is a neighborhood of X, then X is in U. It makes sense. Right, so here, if U is a neighborhood of X, X should be in that neighborhood. That's the first definition. That's the first property. Okay. If V is in X, I should probably pair this with my own notes. This way I can read and I write at the same time to visualize these concepts. Because quite often, reading these axioms so reading this axiom without any diagram whatsoever can feel rather dry. So first, it's just say, if U is a neighborhood of X, then X is in U. X is here. Okay. Second, if V is in big X and U is in big V, okay, U is a neighborhood of X, then V is also a neighborhood of X. So there you go. This is big X, the universal set. Here, if V is in U is a neighborhood of X, so let's draw that. This is U. X is inside. And U is contained in V. V is bigger. So if that's the case, V is also a neighborhood of X. So these are just axioms. Okay, they're just axioms. These are these are not self-evident, but rather foundations of our deduction. We assume the neighborhood behaves this way. It says, the intersection of two neighborhoods is also a neighborhood. Here. So this is X. Imagine it's been covered by two neighborhoods. Say, internet is failing. Yeah, the internet got disconnected for a second. Let's draw 4. It says any neighborhood U is that any neighborhood of U of X includes a neighborhood V of X, such that U is a neighborhood of all points in V. Let's draw a picture. So this is big X. Sorry, the stream was lagging, right? It was frozen for a bit. So hopefully everyone heard what 3 is about. This is a picture. The intersection of two neighborhoods of X is also a neighborhood. So now we're discussing 4. 4 says any neighborhood U of X includes a neighborhood V of X. So this is U. So the idea is you can squeeze the neighborhood, squeeze it down to this is X, this is V. Okay. Any neighborhood V of X can be squeezed down a little bit, all right, so that U is a neighborhood of every point in V. Every point inside V has U as its neighborhood. This is the idea of talking about nearness without actually introducing a distance. So that's why topology is often called rubber sheet geometry. So you're only discussing distance, nearness, without referencing any particular distance function. You can easily verify 1, 2, 3, 4 for the epsilon neighborhood in Euclidean space. They all Euclidean space satisfy 1, 2, 3, 4. And we're just going to abstract those properties and now call them the axiom of neighborhood. So you can talk about nearness without a metric. Okay. The details of this aren't really critical here, but basically these axioms create a logically consistent concept of points being nearing each other. So that's the whole idea, right? Because in order to talk about locally Euclidean, what do you mean by locally? Well, you need a notion of nearness. Topology gives us that tool. Sharing a neighborhood without introducing a distance. Exactly that I was saying. I only mention it for completeness because some of the definition uses it, but you can understand everything that follows if you only have a hand-wavy concept what a topological space is. Okay, so I mean, I hope these axioms can be understood without too much difficulty. Okay, so now we have a notion of a homomorphism. So a function between two topological spaces is homomorphic. It's called a homomorphism is if it is a bijection, 1 to 1 and on 2. If f is continuous and its inverse function is also continuous. So here we are actually not defining what continuity mean. Okay, but let's just accept the concept intuitively. F being continuous. F being continuous, it simply means that you can transform a subset of X into a subset of Y without tearing it apart. That's continuity in a topological sense. So f is continuous and the inverse function is also continuous. It's a fact that from analysis that the inverse function of a continuous function may not be continuous. So here we impose both conditions. Both f and f inverse are continuous, and that's called a homomorphism. Not homomorphism, sorry, that's a different word. Homeomorphism. Homeomorphism. And it's actually a nice visualization down here. Yeah. So you see, you can turn a coffee mug into a donut without tearing it apart. That's a homeomorphism. There's a joke among mathematicians that a topologist is someone who can't tell the difference between a coffee mug and a donut because they're homeomorphic. If there is a function from x and y if there's a function exists between two spaces x and y, then they are said to be homeomorphic. Okay, you can transform the set x continuously into another set y. Continuously meaning you're not going to tear x apart. Okay, bijective means we can associate each point x with a unique counterpart in y. I hope everybody knows that. Bijectivity. Yeah, topologists are horrible bakers. I know, right? They ignore metric information. So all they care about is how many pieces you want, how many holes you want, right? The continuity means we preserve the topological structure around each point. If x and x prime share a neighborhood in x, their counterpart, the transformed version, right, f of x prime, also neighbors. So this is why topology is called rubber band geometry. Right? You can stretch it, but you can't tear it apart. In the process of stretching, if 2 points are close on the original rubber band, they're still close in the stretched version. Right? And the distance don't matter. There's not even a notion of distance at all on its own. And the continuity of the inverse means that this holds in both ways. So homeomorphism means you can regard as x and y as topologically equivalent. An example of a homeomorphism is a continuous deformation. This is a classic example that topologists can't tell the difference between a donut and a coffee mug, since they're homeomorphic to each other. Right? Image is taken from Wikipedia. Okay, the topological space. Okay, finally we can talk about topological space being a manifold. This is a definition of manifold. So first we have the notion of a topological space that allows you to talk about nearness, and now you have a notion of a manifold, which formalizes the notion that in a neighborhood, things look like a Euclidean space. Okay. A topological space M is a manifold if for all point x in M, there is a neighborhood U of x and some integer n, positive integer n, such that U is homeomorphic to a subset of Rn. The smallest such n is called a dimensional manifold. I think now things are getting more transparent. Think about a circle. Right? Think about a circle. Think about a point on the circle. Right? Here. This is a circle. Right. So you can parameterize a piece of arc, an arc of the circle, using an interval, which is of course a subset of R, a real line. So that's the idea. Locally things can be mapped by a homomorphism to a subset of Rn. You see, this is just a one-to-one correspondence. And homeomorphism is continuous one-to-one correspondence. Inverse is also continuous. Right? So there's no notion of distance going on. There's no intrinsic notion of distance assigned to it yet. Okay? The smallest such n is called a dimensional manifold. Think about a map. Think about a map. Let's open Google Map. Perhaps not. There's no need. Everybody knows what a map is like. So this is Earth. Okay. So for example, this is Africa. Okay, like this. Hopefully, this is not too cartoonish. Okay, this is Africa. Okay, and this subset of the Earth can be mapped homomorphism with a homomorphism to a subset of R2. Okay? So that's what it's about. And of course you just need two coordinates. So therefore Earth is a two-dimensional manifold. For each point x, there exists a neighborhood U and some integer n such that U is homeomorphic to a subset of Rn. Okay, I just want to mention that neighborhoods are all open sets. Okay, I don't know why I didn't mention that. Perhaps open set is already implied here. Okay, I haven't checked this, but perhaps you can show. Okay, there's a notion of openness in the topological space. In fact, the usual definition of topological space starts from the definition of open set. Okay, perhaps the axiom of open set is already implied by these properties, but I will not bother checking them. But basically, I want to mention that all the neighborhoods are considered as open sets. They're all open sets. Okay. So here. This is saying that this is a region. This is saying that there is a region around every point on the manifold that can be treated as being Euclidean. This is what it means for a manifold to be locally flat. Whenever you're on a manifold, there is at least a small neighborhood around you that is homeomorphic to a flat space. If U is an open subset of M, then a homomorphism K from U to for a homomorphism kappa from U to kappa of U, which is a subset of Rn, is called a chart. So this is called a chart. The chart can be thought of as a local coordinate system. So this is a little bit different from the parametrization we know from vector calculus, right? Parametrization maps from subset of Rn to the surface, right? Here we're mapping a subset of the surface to a subset of Rn. Perhaps this is more natural for a cartographer, right? So this is perhaps more natural for cartographers. So a cartographer look at a piece of Earth and think about a way to describe it on a plane. So to draw a map, you look at a region and you draw a map. So it's a process that maps a point on the surface to a piece of paper. Right? So this is exactly that process. It goes from a region, an open set of a manifold, to a subset of Rn. And that process has to be continuous, bijective, and the inverse is also continuous. Okay? And this function, right? This function, which includes several pieces of information. Okay, this function includes its domain, codomain, and exact rule of assignment. Together, it's called a chart. So the chart can be thought of as a local coordinate system that associates a unique set of n numbers and real numbers to each point in the neighborhood on a manifold. The manifold cannot necessarily be described by only one chart because of the restriction that U is open. The reason we choose U open is because later on we want to do differentiation, because differentiation hates non-open set. Okay, so this introduces a restriction. So U has to be open and K has to be a homomorphism. So think about, what if you want to describe a circle, right? So to describe a circle, right, of course you just need one number. But the problem is, can you find an open set on the real line, say U, to kappa that maps to the sphere, the circle? The answer is you cannot. You cannot do that. This is a topological constraint, because the inverse map, inverse of kappa, is also continuous. The unit circle is compact. This is a compact. Compactness is a tricky notion, but here you can just think of it as a closed set. Is a closed set and is bounded. Closedness in the sense that if you take limit in the set, it will never exceed. It will never go out of the set, and of course it is bounded. It does not extend to infinity. Okay, so this is a unit circle on R2. It's a compact set. It is a property that under a continuous function, a compact set remains compact. But now think about what happened. So K inverse is continuous. So its image, so the image of the circle under K inverse should be also compact, but U is not compact. U is open. It's not a closed set. U is open. Because you take limit in U, the limit may fall out of it. It might end up on the end point. So this is not possible. So it's not possible to construct a single chart. A single chart just means a single function. A single chart to describe the full circle. You just can't do that. So you need a minimum of 2 charts to do that. Okay, so hopefully this is clear. We have no notion of differentiability yet. Okay, we still don't have, but down the road we wanted to take derivative. That's why we use open set. That's why we use open set, not closed set, some arbitrary thing. Because to do derivatives, you need to move from a point in arbitrary direction. Think about the derivative in the 1D. The limit of f of x plus h minus f of x over h as h tends to 0. This definition is awkward if f of x is defined on a closed interval. If f is from a to b to r, what happened at the boundary? Because x goes to 0 means x can approach 0 from both directions. If let's say, this is I know this is a terrible drawing, but basically at the end point, a, there are certain points, certain ways you cannot extend, or so to say, you cannot move away from a. Right. So that's why differentiation do not like closed set. Open set allows every point in that set to have some wiggle room, and that's exactly what differentiation likes. So we restrict U to be an open set, but this carries consequences. You cannot always cover a manifold using one chart, and that's okay. We're just going to use multiple charts. Just like in real life, we use multiple pieces of chart to describe a region, the Earth, right? And collectively, they are known as atlas. Okay, so there's a great deal of analogy between the definition of manifold and cartography. Sometimes, as I said, a manifold cannot be described with only one chart due to topological reasons. And sometimes it's purely a preference thing. Sometimes you just care about a subset. Now, you don't always need a one chart to describe everything. Euclidean space is special because it has a single chart, just a Cartesian coordinate system. Right. So there may be several possible valid charts for a given region on the manifold. Okay. All right. So chart allows us to do geometry using a coordinate system. Okay. A manifold on its own requires no coordinate system. Chart allows us to do geometry using a coordinate system. Okay, so now a coordinate system is introduced in the form of a homomorphism. Okay, and A is a collection. A is a collection of charts. So A is a set of charts. The kappa is a chart. It goes from an open set UI to the image kappa UI, which is a subset of Rn. Okay. UI is a subset of the manifold. I equals 1, 2, 3, and so on. Actually, I don't know. Do we need a countable? This is assumed that this is a countable collection, right? Do we even need a countable collection? I don't know. Okay, just a bunch of, think of it as a bunch of charts. This is unimportant here. Think of it as a bunch of charts. They together form an atlas. Actually, this is literally called an atlas. We say A is an atlas if the subset covers a manifold. That is to say, the union of all the UIs is big M. No points on the manifold is missed. This is a requirement of chart. Okay. What the hell are we doing? Yes, we are defining a notion of a manifold, a smooth manifold, because this stream is about information geometry. The whole point of information geometry is to understand probability distributions as manifold or curved surfaces if you want. So here we're trying to give a formal definition of a manifold. We've seen some calculations earlier from an informal standpoint. Allows you how to calculate distance on a manifold, but here we're actually giving a more careful definition of manifold, which is this part. Okay. Once again, this is purely geometrical. Okay, and this is interesting. We call the functions, what the heck is this, right? This is called the transition map of the atlas. Let me draw a picture for that, because this is a little bit subtle and actually quite important. Because when we later on talk about smooth manifold, we're actually referring to the transition maps being smooth. Let me actually draw the picture here. Okay, so this is the manifold, which I represent as a donut, as usual. My favorite snack. Okay, and here you have, this is a region. This is the region. This is one subset. This is big M, okay? And this is Ui, is a subset of M, open set. And of course, it is a part of the chart. Ui is the domain of the chart. Say Ui gets mapped to kappa I. Right? So the kappa I maps Ui to a subset of Rn. This is Rn, which I visualize as a Cartesian plane. So this is kappa I of Ui, the image of Ui under the homeomorphism kappa I. Okay? That's cool. And now you have a separate region. Not necessarily separate, but just another region. Okay? It may have overlap with the original. Actually, let me change color. Called Uj. Uj may overlap with Ui. Think about in real life how a map of Europe and Asia have overlaps. Like Russia is a country that's both in Europe and Asia, also is Turkey and perhaps others. My geography is not the best. But anyway, the idea is it is entirely okay to have UIs that overlap in the atlas. Okay, so now you have a separate, another chart, right, kappa j, that maps uj in a homeomorphic fashion to another set. So this is kappa j of uj, also a subset of Rn. So we assume this n is the same for all the charts. You see? Here, it doesn't matter which chart you're choosing. The image is always in Rn. N is fixed. So you can't just say, oh, one region is homeomorphic to a region in R2, another is homeomorphic to a region in R3. That's messed up. That's not a manifold. Okay? We assume n, the dimension, is consistent. So what happens in the overlap region? Right? What happens in the overlap region? So think about the overlap region. How is it represented in each chart? We know, let me highlight this. The highlighted portion, this is here. This is the overlap region. This is UI intersect UJ. Okay, under the map, KI, let's say it gets mapped to here, on this copy of Rn. Okay, so this is kappa I of UI intersect UJ. Intersect UJ, okay? All right, and we do the same here on the other chart. So this is kappa J of the same region on the manifold UI intersect UJ. Let's highlight that as well. Okay, the transition map, as the name suggests, allows you to transition between the two regions. So how do you transition? How do you go from here to here? Well, take a look at the diagram. You want to go from Kj, right? So Kj, you want to go from this region, Kj of UI intersect Uj, back to Ki UI intersect Uj. What do? You invert Kj. By inverting Kj, you get back to the manifold and then apply Ki. That's exactly what happened. Invert Kj and then apply Ki. That's the transition function. So that's the transition function. You see, start from a point here. Using the inverse of Kj, you get back to the manifold. That's why there's a Kj inverse. And then apply Kj, you're back to another piece of Rn. Okay, so the transition function is a map from a subset of Rn to another subset of Rn. the nice thing about that is that you can do calculus here, because M is abstract, remember. We don't even know what M looks like, let alone doing calculus here. But here you have the transition map. The transition map is a function and maps from a subset of Rn to another subset of Rn. Certainly you can apply multivariable calculus. So if the transition map is differentiable, we will say that M is a smooth manifold, is differentiable manifold. If only the transition map is continuous, it is called a topological manifold. You can only talk about continuity, but you may not always be able to do calculus here. If the transition map is differentiable, we call the manifold is a smooth manifold. Right? And as I said earlier, Riemannian manifold is a special kind of smooth manifold. You can do calculus there, and you can also do geometry there. Right. So the transition map dictates the type of manifold we're talking about. Okay, I haven't been reading chat. Is there anything new here? Okay, awesome, great. Let's continue with this definition. So this is a very careful definition. Okay, even though things like, for example, continuity is not completely specified. Okay, but we're getting the main structure of the definition. Okay, so what we mean by a manifold. Does the loss landscape in neural network live this kind of manifold? Good question. Good question. So the problem is, now you come back to the question of applicability, right? This is a very subtle question, and not always. Not always. I was just reading a book, actually. Let me digress a little bit, right? Because at the end of the day, we're practical people, right? We wanted to apply this stuff. This is beautiful mathematically, but how is this going to make our lives better, right? So I was reading a book here. Maybe I shouldn't show this, but here, it's called, I cannot show the book because of copyright reason. I do have a physical copy of the book, but anyway, it's called Algebraic Geometry and Statistical Learning Theory. It's not differential geometry, it's algebraic geometry, and it's very interesting, also written by a fellow Japanese mathematician. So the reason we also use algebraic geometry in probability and stats is because sometimes our model of interest cannot be easily incorporated into the differential geometric framework. So for that, you need, I'm not going to pretend I understand this stuff, okay? I'm just still very much a beginner myself. So here, this is a screenshot from that book. This screenshot from that book. So in the earlier part of the stream, we emphasize that we assume non-singularity of the Riemannian manifold. That is to say, you can always the distance, right? The distance between two distinct points is always positive. But in certain situations here, you have singular statistical model. You can have two different coordinates that has zero distance, including layered neural networks, radial basis function, normal mixture, binomial and multinomial mixture. Yeah, mixture model is a big topic, and it does not fall into the category of differential geometry very well. Reduced rank regressions, Boltzmann machines, Bayes network, hidden Markov model. You see, not always. Right, so that's why, as I was saying, first of all, the mathematical machinery for this geometric paradigm of statistical machine learning is very formidable. But on the other hand, they don't always correspond to even some of the most well understood models here. For example, hidden Markov model is very well understood, and the differential geometry theory does not accommodate that very well. Sorry, what book is this? Okay, sorry. This book is called Algebraic Geometry and I'll just type it here, Algebraic Geometry and Statistical Learning Theory. Here, yeah, this book. I was just reading this one. I was trying to have something to say about the limitation of information geometry. Yeah, so yeah, I believe the author, Sumino Watanabe, is a colleague of Professor Amari. So, and yeah, here we have singularity theory, algebraic geometry, zeta function, singular integrals, empirical process, things like that. So these are geometric models, geometric interpretations or geometric formulations of models that don't have a straightforward differential geometric formulation. With information geometry, we can determine what distance and curvature in model parameter space mean in the first place, right? Hang on, let me reread this. With information geometry, we can determine what distance and curvature in model parameter space. Yes, that's what basically what we're talking about. And of course, in a restrictive sense, okay, in a very restrictive sense, you have it all depends on what kind of model you're talking about. So if, let's say, we're dealing with which one here? No, yeah, in this paper, right? We start from the classical setup, a parametric scenario. If a distribution is specified by finitely many parameters, then under certain regularity conditions, you can define the metric tensor. The metric tensor allows you to calculate length, volume, curvature, that kind of thing. Okay, so this is really cool. This is fascinating. It is very enticing, right? The mathematics is very elegant, but the thing is, unfortunately, it is not. The reality is complicated. Okay, it's very easy to get enchanted by the beauty of mathematics, but at the same time, its applicability remains somewhat limited. And actually, guys, you know what? Because we're nearing the end of the stream, I'll give the content list. I'll first give the content list and see if we can finish the definition of manifold in that gentle tutorial. Okay. So the content list by Professor Amari's book. Let's just see what kind of applications that are promised, okay, in this exposition. Okay, so this is part 1 of the book. Perhaps actually, you know what? Maybe I can just search it online. This way, it will save me some copy and pasting here. Information Geometry and Application by Amari. There you go. Yeah, so this is a book. Go here. Do we have the Springer link? Yeah. So this is what's promised here. So actually, the first part is readable without specialized differential geometric background. Okay, the first part is actually very readable. Manifold divergence and dually flat structure. By the way, dually flat structure is arguably what's unique about information geometry compared to traditional differential geometry, because traditional differential geometry has no such concept, dually flat structure. Okay, this is something unique to information geometry. Exponential family and mixture family of probability distribution. The theory of information geometry works very well for exponential family. Invariant geometry of manifold probability distribution, alpha geometry, blah, blah, blah. And this is part 1. Part 2 is Introduction to Dual Differential Geometry. This is an informal introduction to differential geometry. And now here comes the application. Information geometry of statistical inference. Asymptotic theory. Estimation in the presence of hidden variables. So this is EM algorithm, basically. Expectation maximization. And it has a nice informational geometric interpretation. So EM algorithm, on the surface, in its ordinary exposition, feels rather abstract and unintuitive, and it actually has a geometric meaning. Using the notion of dual differential geometry. So, and also the Newman-Scott problem, linear system and time series. Application, machine learning, natural gradient learning and dynamics in singular regions, signal processing and optimization. Okay, that's pretty much the book. Okay, so here you can perhaps even look at more detail here. Do we have, this is a chapter. I want to see the content list. Can we see it from here? More detailed content list. Okay, here. Yeah, this is a more detailed content list. Yeah, you can go to the Springer website and check it out. Okay. Anyway, so in particular, let's take a look at the application part, because what's the prize, right? Asymptotic theory. This is classical mathematical statistics. And EM algorithm, as mentioned, Newman-Scott problem, linear system time series, geometry of AR, MA, armor model. If you've done time series analysis, this is very classical. Machine learning, including clustering, geometry of SVM, stochastic reasoning, information geometry of boosting. So boosting is also quite popular nowadays. It allows you to combine the power of weak learners into stronger learners. So this is a very high level talk. I usually don't want it to do this kind of thing because I feel like I'm not really saying much. So the idea is you want to combine weak learners into a more powerful machine, so that you can overcome the bias variance trade-off. So nowadays, with the help of boosting, you can increase accuracy and also reduce variance. Natural gradient learning and its dynamics. I have no idea what this is about. Perhaps because I haven't looked into the part 2 yet. Okay. Signal processing optimization. Okay. Seems like you have something to do with PCA. That's pretty interesting. Okay. So overall, this book do not assume a background in information geometry, and the treatment is mostly informal. Okay, so for example, in the differential geometry part, there's no definition of a topological space. Okay, so part 2, elements of differential geometry, manifold and tangent spaces, Riemannian metric, affine connection. These are classic differential geometry, but they're introduced in an informal manner. And there's no exercises. You know, the thing is, you know, as Euclid said, right? There's no royal road to geometry. There's no royal road to information geometry either. Okay, Amari promised you can learn this stuff without tears, quote unquote, without tears. I have doubt about that, but perhaps treat this as a source of intuition and try to look for the relevant definitions. Okay, relevant formal definitions to actually be able to work with this stuff. Yes, it sounds like the book offers a new look on old topics. Exactly. Christian, you nailed it, right? So that's why, you know, despite the initial hype, despite the initial hype, the mainstream statistic community, data science community, feel like, these are nice things, like, for example, interpretation of the EM algorithm. But, how do we go from here, right? How do we go from here? Perhaps, once again, I mean, if something is written in a textbook, then it's probably already established. There's that, right? So why don't we look at another paper, which is also in the stream description, by Frank Nielsen, I believe. Here, it's in the. I think I downloaded that one. Let me find it real quick. Elementary information geometry. Hang on. No, not this one. But basically, I have another paper. No, not I have another paper. I haven't written zero on this stuff. But there's another paper. It's called An Elementary Introduction to Information Geometry by Frank Nielsen. Yes, this one. Yeah, this is also a highly cited paper. It says it promises elementariness, but as you will see, it's still quite. It's just the nature of the subject. It's very forbidding. Okay, when it comes to the prerequisites. So basically, here, let me just see if there's any new results or extension or whatever being promised here. In this survey, we described the fundamental differential geometric structure information manifold. State the fundamental theorem of information geometry. This is actually much harder, okay, much harder than the first paper we've seen. But I want to see what kind of new results are available. So this is closer to research literature rather than pure pedagogy. Okay, outline of the survey. Okay, outline of the survey, what do we have? Okay, you have, in the first application, we consider the problem of Bayesian hypothesis testing and show how Chernoff information can be geometrically characterized. Oh, wow. In the second application, we show how cluster statistical mixtures share the same component distribution. Huh. See, not easy to understand what even is being accomplished, right? Not very easy to understand what is even being applied to. So these are in the paper. Once again, here it assumes quote unquote no background in differential geometry, but I guess to be able to work with this stuff, you still have a lot to overcome. Okay, so hang on a second. Where's the application? I mean, it is. You got this vague list of application. We've seen that from the Wikipedia article already, but perhaps there's something in this one, and I haven't read this through. Okay, because I don't have time. Anyway, coming back to the end of the paper, is there anything that is not, already well understood in the classical sense? Huh. Restricted Boltzmann machine, neural manifold, and natural gradient. And it apparently has application in optimization as well. Barrier functional interior point method. So these aren't statistics per se, but this is optimization. Okay. Natural gradient in a Riemannian space. Actually, I heard that this natural gradient business is one of the main reasons that information geometry has been gaining more traction in recent years, because the development of this subject is very, how should I say, it's not smooth at all. So as Amari himself put it, he initially he was trying to publish paper in the 80s and was rejected by top journals because the editors say there's nothing can be said about differential geometry in statistics. They just didn't believe it was possible. And at the same time, remember here, oh, not this one, but yeah, this one here, because of this notion of dual differential geometry is unheard of in classical differential geometry. The editors rejected it completely. They thought it was just something that's made up. So his paper went, because he couldn't even get publication for many years until like the mid 80s. So I know I'm rambling because I don't have a firm understanding about this at all. So and quite frankly, I don't even know I should study this seriously for this to is it profitable enough for me to study it seriously? I don't even know. Okay, so I know I'm sorry if that comes as a disappointment for you guys, but this is what it is. Okay. Actually, you know what? Why don't we conclude this with a historical review? So, Professor Harold Hotelling first devised the notion of Fisher information matrix at the Riemannian metric tensor, what we did today. His handwritten note, this wasn't published, okay? So this is a handwritten note. And sorry, it was only fully typesetted a bit later. So he had this idea, Hotelling had this idea, but it wasn't publicly known. And then Rao published his paper, which included his famous Cramer-Rao inequality, CR-Rao. In the celebrated paper, it also includes the CRLB and the Rao-Blackwellization. These are now well accepted. Cramer-Rao and Rao-Blackwellization are standard material in mathematical statistics text. It's quite amazing that information geometry, the fundamental idea of information geometry, was among them. So the Riemannian metric distance is called the Fisher-Rao distance, or the Rao distance. Okay, but things kind of went dormant since that. In 1960, Nikolai Chentsov studied algebraic category of statistical decision rules, which induce geometric structure. Right. So earlier, remember how we explained informally this invariance, quote unquote invariance, restricts the form of a metric. And it turns out that the Fisher information metric is essentially unique. It's the unique metric that satisfies the invariance. Okay, and then however, in the original Russian monograph, Chentsov used the Russian term. Why is there a little r? Is that a typo? Yeah, it should be capital. Geometral statistics. That's the Russian term for information geometry. So it went completely unnoticed in the West. And now next up was is Amari's contribution in his 1985 monograph, and he actually coined the term information geometry. Okay, and now the term sticks. So started in the 80s, there were more attention to it, but then once again it kind of went dormant until the recent decade. Okay, so with that being said, like if you wanted to seriously study this field, what do you need? So in my opinion, I guess you can just follow Amari's text. That's perhaps the most approachable way. That's just just following this, because and don't worry about the uh, the differential geometry detail unless you finish part one, I believe, or at least mostly finish part one, because a lot of the information geometric notions can already be understood without things like parallel transport, curvature, like that. And in particular, pay attention to the notion of divergence. Divergence on its own is also very useful, not just in information geometry, but information science. It's called relative entropy. And actually, there's this paper that we ignored, we skipped through, is that you can actually derive the Fisher information metric based on relative entropy, S. S is a relative entropy, also known as the KL divergence. Relative entropy here. S, where's S? Yeah, this is the KL divergence. So divergence, relative entropy are also used elsewhere. So if you wanted to study this, first of all, prioritize divergence. And for divergence, there's already something you can do with divergence directly. You don't need specialized differential geometric tools to talk about divergence. For example, the divergence already have geometric results called the generalized Pythagorean theorem and the projection theorem. So this is already pretty useful. And of course, exponential family, this is a highlight. This is one of the great, I wouldn't call it perhaps success. You can call it success. Yeah, I think it's fair to call it success. So basically, the information geometry works beautifully for exponential families. And I haven't read the rest, to be honest. So would I recommend it? I would put them like a mid. I pretty much established it from the beginning. Let's say if you're advanced undergraduate student or beginning graduate student and you wanted to study the mathematical part of data science, machine learning, probability, and whatnot, I think you should still prioritize things like measure theory and functional analysis before going into sailing full speed into differential geometry. Okay, so I think this is the cherry on top. Bottom line is, so still, it can be useful, but the undisputed mathematical, the king of mathematical machinery in data science, machine learning, is still functional analysis. It's still functional analysis and measure theory. So you can't go wrong with that, because after all, I mean, mathematics is beautiful. We know that for sure. But our life is also short, right? So it's all about bang for buck. So should you prioritize it? I would say not until you have known measure theory and functional. Okay. So that's all I got to say about that. I mean, of course, that's my opinion, and you feel free to disagree with it, because I'm not even vaguely well versed in this area. But it's fair to say that's the attitude of perhaps a lot of the practicing statistician, data scientist also. So that's all I got to say about that. It's beautiful, for sure. Is it useful? Is it as inevitable as the first paper claimed to be? I put a question mark there. Okay. Thank you very much for watching. But of course, I will continue making videos and streams on tensor calculus, differential geometry, as well as perhaps we'll see some information geometry there. I don't want to sell this. I have perhaps, and actually it's interesting, because I've been asked to make content on information geometry for a long time, ever since my channel picked up some momentum. Because my channel earlier, the videos that got most views are the is a series called geometry of statistics. And over there, we used not information geometry, but rather L2 geometry. So quite literally, we're doing functional analysis without naming functional analysis. So just come back to my original point. You're better off studying Hilbert spaces, but like the thing is, if you haven't studied Hilbert spaces, you should do that first before touch information geometry. Okay? And I don't think there's any kind of bias in that, because Hilbert spaces, the usual Euclidean geometry, is just too powerful. Anyway, thank you guys very much for watching.